We're gonna cheat on this, baby. So what you do is you line up a piece of paper or something with that circle, and you've got the along. In this case, our enthalpy lines, they're nice enough, they're on straight here out here. And on the other side, there's going to be an enthalpy reading or whatever, chart reading that matches this, we'll get over here somewhere. Because in this case, it's down here somewhere. And it's kind of nice to have an idea about where you're looking.
I failed y'all again, we have rulers as well.
Oh, super. Man, last time we didn't have those.
Yeah, this is.
Yeah, so what you do in real life, because they won't do that little line. Just line up. So you finally get the numbers, the same on both sides.
Yeah, exactly. It's not gonna line up perfectly.
All right. So now we know from that point, those two pieces of information, we've gathered two more. So we know that we know what our enthalpy is now. And there's, my goodness, it looks like 13.5 almost goes through that. Now those lines have a pretty serious slant. Good. And they're a little bit hard to see, but if you look, you can find a 14.0, and you keep going down, and you'll find some others like that. You want to find that it's a little harder to find on this one. There's the yeah, there we go. Yeah. There's 13.5. You see the next one is that. And so it's in between there, and that's how we got our.
Just so everybody gets what we're doing in case this got missed. What we're trying to show you here is that once you know any 2 points, you know all the rest of these. We're just kind of going over where each of them are. So you can use any 2 to find the rest. Once you get that point, you find the rest.
Yeah. Okay. Okay. All right. So we got that. And we can extend the line over, and we discover that our dew point is 52.2. And as I said, that is going to be exactly parallel with the next one here. Absolute humidity. And so let's look at what happens if we go to the air handling unit now. So what happens is our big question. What happens is air flows through the air handling unit prior to being supplied to the occupied space. So here we go. Sensible heating. There's a mixed air temperature. There's a supply air temperature. And because no moisture is added to it, it's a straight line. All you do is heat, no moisture is added to it, and it's a straight line. On the back, to review this, there's stuff in the back that covers this too. So heating doesn't add or remove moisture from the air, and the same is true for cooling when the cooling surface is above the dew point. But most of the times when the air conditions not, moisture is not added or removed. There are parts of the country, like here, where a good deal of the year, moisture is not removed from the air because the air is so dry. Getting in Nevada, some places even more so. So cooling and dehumidification, what does that look like? Well, there's our return air, there's our outside air, there's our mixed air. And you notice we cool, straight sensible cooling until we get to a place where condensation in the coil starts. then it starts going down like that. So this area right here, if you look over there, we have so many grains of water. Down here, we have less grains of water. Okay. And there's our process that takes us from the cooling coil discharge through the room, back to the return air, and where we go back to finally through the ductwork and where we mix. So when we cool, in most parts of the country, most of the time, we're going to remove moisture from the air. So here we have cooling with dehumidification and reheat. Mixed air there. We cool, come through our coil, get down to the supply air temperature, or really it's the coil discharge temperature. Then we reheat it. And then we take it to the space. And the reason we do this, and we're not getting into this class, but in order for us to hit what it's supposed to be in the room, this angle is going to stay the same for whatever room conditions we got. And so for any design condition, that line is going to be constant. If we came off the coil like that and back into the room, our humidity would be way down here somewhere. And we'd have a problem with being too cold. Well, wait a minute, our humidity, what I'm saying is our temperature that we hit the room with would be way back here. We wouldn't be able to get the water out of there. I'll just back off the stove. The room conditions would be screwed up, it'd be too cold, okay? And so in order to keep from that happening, is we took it way down here, and really in order to have this match that, we had to reheat it to that, all right? So that's why we reheat. Otherwise, the room gets really cold. So here's the best way to think about it. We cool the air as much as we have to get the dew point that we're after. After that point, the air is too cool to be getting used to the room because it's too cool. So we bring it back and reheat it in the air handling unit to the point where we can discharge it to the room and it not be too cool. Now, there are different ways of doing that. We use heat wheels, we use runaround coils, we use all kinds of things, including the reheat, to do that. So that's its purpose.
Not a waste of energy.
It depends on your energy source, but if you have a process that requires it, it's not an option. Labs, for example, have to be a 30% relative humidity often, or 40, and it can only vary plus or minus a few. You got to do it.
So yes, to answer your question, it is a waste, and there are rules that will allow you when you can and cannot waste.
Yep.
Okay.
Just one of the times you have to.
You're supposed to try to use free recovery energy if you can.
Yeah.
So like in the case of a dedicated outside air unit, you think about a lot of times you reject heat to the outdoors with the air conditioning system. You can actually reject some of that heat back into the airstream. That's kind of a free way, if you will, to recover that heat.
Yeah. And it reduces the overall work that the compressor does too. So there are things like that. So you can use waste heat. But okay, total heat is equal to sensible heat plus latent heat. We talked about that before. BTUs per hour is 4.5 times CFM times change in enthalpy. That was that thing we measured last. And so here's an example. We've got 10,000 CFM going through a cooling coil, entering air temperature 90, 76 wet bulb, leaving temperature of 55, 53 wet bulb. We're at sea level. Good. Find the amount of total sensible and latent heat transfer. So here's our picture of what this looks like. So the BTR is going to be 4.5 times the CFM times change in enthalpy. And that gives us 4.5 times 10,000 times our change in enthalpy. Coming in was 39.4 and living was 22. And we got that over the cycle chart. I mean, that's what we would do. And then the answer is 783,000 BTUs per hour. Okay, sensible heat. BTUs per hour times is equal to 1.1 times CFM times the change in temperature. Now again, this is just the temperature that you feel. Now that gives us, when we're all finished with those, 385,000 BTUs per hour. Now remember, we're missing the component. That's the latent. Latent heat is equal to sensible, total of sensible plus latent So what we can do now is we can subtract the sensible heat from the total heat, and that gives us the latent. Because remember, we figured out one for the total. That one right there. Now we did the sensible, and we'll subtract, and we'll know what the latent heat is. So we ended up with 398,000 BTUs per hour latent. So you can compare water side cold data to air side cold data from the tab report using heat transfer, even for a cooled coil. That's the whole idea here. We saw you do it with heating coil. You can do it with cooling coil too. You got to take both heats into account, because total water temperature change is going to be, it doesn't know about latent and sensible. The water side just knows about temperature change because it stays water all the way through. Total heat total heat loss side on the air side equals heat gain on the water side. The BTUs power for air are going to be the same as the ones for water, and the heat should be balanced. We talked about that a little bit. So, a review, we talked about the compressibility of air and water. Air very compressible, water hard. The density of air has an impact on heat transfer, and that the more density areas, the more it can carry. And it also impacts the velocity measurement, and particularly on pitot tubes. The elevation also affects density because of pressure. Air or water flow can be determined using heat transfer equations. And we can prove supply airflow is proportional to sensible heat that's removed or added. That's the airflow. It all depends on what we're taking into or putting into. Taking out or putting in. Calculating airflow from the duct size and velocity is that we've got, if we have an area and a velocity of the air going through it, we know how much CFM we got. The use of pitot tubes is really common. We also have another thing that's used. It's called an airfoil. Uses the same principle, just slightly different, but the same idea. Conversion of velocity pressure to static pressure. I'm sorry, yeah, velocity pressure and velocity. We have the formula for that. Have that square root thing there. Calculation of outside air for mixed air properties. Actually, what you're doing is finding mixed air properties are going to be the average of the weighted average of the incoming stuff. So if you think of it like that, then it's pretty easy to come up with what your mixed air properties are. We've talked about the air-water vapor conditions, and we've used the site chart to find them. And we've used some of the equations there to determine the cooling coil performance. And Tuesday, and try this again. Wednesday and Thursday in the lab, you'll go through these things even more so. Our intent there was to be sure that you understood the words you're going to get hit with. And believe it or not, a couple nights sleep before you hit it really clear stuff up. So, okay, I think I take a break for, is it lunch?
A little behind, I would say no. We've got another session before lunch, so I'll just ask, please take a 5-minute break.
5-minute break, okay.
Yeah, so no, I understood that. That was completely less. I would have been all there. Chad.
Still got 3 folks missing off of the roster. Everybody sign this. Got 28 signatures and got 31 people in here. Ready? Make sure not you. Yeah, I think there was another.
Yeah.
So we've had a couple of folks ask about the Wednesday potential holiday. I have zero guidance from Huntsville on that. Follow whatever your district tells you to do. So far, I have not received any instructions. That I can't imagine we're going to cancel class for that. But I have zero input on that. If your district tells you to do something, then do whatever they tell you to do. But I'm going to be here
For Wednesday.
for Wednesday, right? Yeah, they're talking about a holiday. And I don't know.
It was for the president.
Correct.
National Day of Mourning.
National Day of Mourning, but I guess they're going to make it a federal holiday. Talk to your timekeepers or whatever. I don't have any guidance I can give you on that. Sorry. I'm going to plan on being here and going through the labs.
Except for labor, even labor in all these cases was already spent last year, so I'm always amazed at the things they do to decide not to spend the money up they're spending.
I'm here. I came to find.
Like I'm on a show that guy, you know.
I'll get my day another day. Just eat one
Okay, I'm gonna go ahead and get off here, even though. Don't fret, we'll be okay. We're gonna be describing the major types of HVAC systems that we use in DoD. We're gonna identify major components of the systems, describing their functions. We're gonna look at the fan curve, equipment schedule, and equipment nameplate. We're gonna locate the operating point of a system, given the fan curve, airflow, and static pressure to evaluate the selection. We'll note the differences between constant volume systems and VAV systems, pressure dependent and pressure independent systems, the most widely used standards for duct construction, pressure and duct pressure classification, and then fan testing and rating. We have central systems, or you start with an all air system. And I think of the ventilation we do for mechanical rooms very often, just fan and moving air. Sometimes we have duct with the fan, but basically there's just air. Then we have air hydronic, where air transfers its heat to the hydronic system or picks up heat from the hydronic system. We have air electric, in which the heating element is electric. We have all hydronic, and then we have all electric, and finally the unitary systems. The unitary system, we'll talk about those in more detail, and you'll see what that's all about. So major components of an air handling unit are a mixing box, filter section, conditioning apparatus, fans, and then we have off of that, distributing it, is the duct system. And here's a typical air handling unit, and we've kind of seen this picture before. Here's where the air comes together. We call that the mixing box. There's probably some other terms for it. Sometimes it's mixing plenum. The concept is it's supposed to mix there, and the reality is it may not. And generally what we find is that if it doesn't mix, you can have a layer of really cold air go through here and go through the fan, down the ductwork, and surprise people. So just know that just because it's called a mixing box doesn't mean that it mixes. The fact that it goes through the fan doesn't mean it's going to get mixed either. So the mixing box provides, what is that location? It doesn't provide a means. If you're really sure you have to have a means there, you have to put a means in. There's various things that are used to ensure mixing, if that's critical. And also it's supposed to provide a means of mixing outside air with return air to from space. Dampers are proportional. In a constant volume system, I guess you could say manually or automatically, the return outside air, but because we usually control mixed air temperatures and use some form of, in most good deal of country, we use economizer cycle. They're probably not manual, almost always automatic. And then we have a minimum outside air setting, and we may have an economizer setting. our economizer range. So we're back at our system again here. We've got an exhaust air fan taking some air out of the building. That runs usually somewhat constant. There are intermittent ones depending upon its function. And we've got the pre-filter, the filter, and we've talked about those. Those are the ones that are usually where our current approach is 8% MERV there, MERV 8 here, and 13 there. Filters, standard 52.2 is the controlling one. Minimum efficiency reporting value, that's the MERV, stands for minimum efficiency reporting value. MERV 1 is really low, we don't use that. Well, we might under certain circumstances, but in normal HVAC use, we wouldn't use that. There are conditions in which we suggest that for a certain application. It goes up to a MERV 16, which is 95 plus ASHRAE filter. The total performance of the filter air in tandem with its holding device, what we're trying to say there is that a filter and its holding device have to be viewed as a unit. And in essence, the filter is not going to be a whole lot better than that which holds it. If it's held in such a manner that it leaks, air leaks around it, the filtering is not happening that's supposed to happen. We'll still may get some filtering, but we have a lot of stuff going around the filter. So that's why we say that the total performance is also a function of the holder. So in order to get what you need to for filtering, you have to be sure that the holding system is leak-free. Here's different filters. We have viscous impingement. These are often seen in the residential applications. You can see through them. The idea is that dirt crashes into the fibers and it's coated with sticky stuff and it sticks. Another thing that they do is they build up a filter cake. That's really what ends up being the filtering element is the filter cake. That's true for all filters. Let's go on to the electrostatic precipitation. That's not true for them. They take the stuff out of the air by electric charges, and they're pretty effective. I have some at our home. You gotta clean them a lot. They're kind of hard to clean, but that's electrostatic. Bag filter gives us extended surfaces, which amounts to lower velocities through the filter, which gives us, for the same amount of filtering, lower pressure drop. Then we have the HEPA filter, and that's for the high efficiency requirements we sometimes have. And then the pleated media. Most of our filters are pleated media, and just so you know, you really increase the life of a filter when you go to a deeper one. A 4-inch pleated filter has much more life than a 2-inch pleated filter. The reason is the pressure drop through a filter is a function of the resistance of the filter and the velocity squared of the air going through. So if I have 6 feet, let's just say I have 2 feet of filter, and I replace it with something that's got 4 feet of filter, I have just reduced my pressure drop through that filter greatly. Now, another thing that I've done is increase the life of the filter because I changed the filters at a certain pressure drop. And now, because my flow rate through the filter is lower per unit area of filter, I can carry more dirt before I get up to that place where I have to change it. So it's something to keep in mind. We don't always have the option. On rooftop units, we're stuck with an axle on a 2-inch filter. And sometimes that won't get us through tap, depends on where you are. So the conditioning apparatus is, in this case, it's the heating and cooling coil. And cooling is where the dehumidification occurs, if it occurs. And with, I'm just going to limit that. Then we have after that reheat, or sometimes we have to humidify. And so we will do that usually downstream of the fan if we can to make use of the energy input from the fan heating the air. Sometimes we'll have to put in a heating coil in that spot. And then there's the fan, kind of the heart of our system. And it moves air by basically bashing into it and making it move. People say it's centrifugal, that's what we call it, but actually it's another force that makes it move. Because what happens is air is like this, the fan crashes into it like that, and moves it like that. The air does not necessarily mix as it goes to the air handling unit unless it's way off of its curve. The air goes basically radially out from the center. Very low spinning occurs. That's why you can have, if you have bad stratification, it'll go right through your fan, hit the duct the same way it came in, and going down the ductwork. So types, we have centrifugal, squirrel cage blowers, various types, and then we have the vane axle, which is a wheel with big vane-like spokes, and then we also have what we just call the prop fans, which are usually not real props. Standard for testing and rating is the AMCA, so we almost always ask for our fans to be AMCA rated. It's a big deal. Here's a bunch of different fans. And this one right here, we're seeing a lot more of. It's called a plug fan. And in an air handling unit, this would be the side towards the coils and stuff, and this would be the side toward the discharge. And they don't have a shroud on the outside. And I'm not going to get much into those things, but there's pluses and minuses. Here's what we call a fan wall. And we're seeing more of that. There's a lot of pluses and minuses in those too. And currently I'm seeing a lot more minuses than anybody had anticipated. But that's not a part of tab, just that there's pluses and minuses for all fan types. Vane axle is this one right here, which is very similar to one called the tubing axle. And all I want to say is the tubing axles and vane axles look a lot the same, but there are some differences, minor differences that differentiate them. Here's a typical, what we call centrifugal fan. It's a backward incline. And so the thing rotates this way, and you can see the blades are slanted so that it rotates like that. That's the backward incline. And here's some typical parts. And we got the inlet collar. This is called the impeller, say whether we use for pumps or sometimes wheel rotor. And there's this thing right here. If you look at your student manual, you'll see this. And part of the purpose of that is that hopefully you'll be able to use that as a reference material. And you'll see they have several different names for the same thing, just so you know. And if you want to look it up, that's a good place to find it on that side. Fan performance curves. Really important when you're selecting the fan. You don't get to do that, but when you're trying to do test and balance, once again, it's really important. This one right here is a 36-inch backward inclined, and I've got what the SW is. Single width, I think it is. Single inlet fan. This is right here. Pressure class is kind of important because a lot of times if we can't make the pressure that we need to have, we'll speed the fan up. Well, class 1 on this side, on this fan, 1073 is your max RPM. Go over that, you run the real risk of everything blowing up like that, because they will come apart. Class 2, its limit is 1400 RPM. Just quickly go through what we're looking at here. We've got horsepower lines, those are the red ones. We've got the CFM, multiply times 1,000, know what you got. And then here is a static pressure in inches of water. Okay. I don't think I got impatient on that one. Okay. So this line right here is the one that you never want to go on this side of that line. And the reason is because you get into what we'll just call stall territory. Because the airflow is, you don't have enough mass through the fan in order to maintain the airflow of those pressures. And you see it kind of stalls out and goes flat. It's really kind of worse than that, and you'll get the fan going loop, 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 loop. And that's because of the air going in and out of the fan vanes. In time, you can't fatigue. And as in the design, we really highly recommend you stay away from that knee. And the reason is because when you do test and balance or install the plane, it's not unusual to have to speed the fan up. And if you're too close to that knee, you're over here in no time flat. So fans should be selected, when you see things come in, they should be selected down on this part of the curve.
So what causes that?
That blub, blub, blub sound.
Right.
It's actually air surging in and out of the fan blades. The fan goes into surge. Same thing in aircraft experience.
You're starting the thing.
Yeah, that's another word that's used. But it's actually physically, what happens is the air pressure outside of the fan gets higher than the pressure that the fan can build by transferring the momentum to that stream of air. And so it comes back through. And it just, it's kind of usually kind of a low frequency thing. It can be a little higher, but usually it's kind of a low frequency.
So the fan would be too small for the motor?
No, the fan is poorly selected. it was selected too close to this line here.
We have an old theater that has this massive fan, and they ran into that problem and blamed it on a bearing issue.
Well, I could, bearing and construct could change things, but
Yeah, but what we found the solution was to slow the fan down.
okay. So,
So in that situation you're describing with the, like, I'll keep wanting to say slugging.
Yeah.
They're essentially moving the same volume of the air then, because it's sucking it back through.
well, because of the mass of the air in the duct, you will have a flow rate that is going to be something of an average. Because it will, what happens is, the airflow rate instantaneously reverses, but the airflow in the duct is still going, so the pressure right here drops. And now it comes through again. The pressure comes back up, and then you go into a stall condition again.
There's another problem too. So you got that issue, which is the pressure on the discharge of the fan. It's a pretty technical subject, what he's talking about with the, that level of surge. The other problem that you can have here too is if you look, I can go look at any point right here and say, all right, this fan, if I'm, and he hasn't got there yet, but I just want, while we're talking about this, this is called the flat portion of the curve. If I look right here, get the pointer so I can get out the way. If I can, on this sloped portion of the curve, he's gonna talk more about this in a minute, I can look over here and see my static pressure is this, and I can correlate that to a flow rate. Anywhere over here, I'm more on a flat portion of the curve, like, so if I'm operating at 5.5 inches of static pressure, that can correlate to any flow rate realistically from 0 to 6,000. So I'm also unstable in terms of this fan is wanting to move on its flat portion of its curve. So there's two separate issues there. Does that make sense? You got the physical construction of the fan, which is part of where this number comes from, and also you never want to be on this flat portion of the curve because you got multiple airflow rates that this fan can potentially operate at the same static pressure.
Yeah. And that's part of how you get that bloop, 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 bloop kind of sound.
Hope that made a little bit of sense. Maybe not.
So, yeah, and thing to watch is that very often sales guys will sell you on, well, look, it's going to go through the duct anyway, and you know it's going to correspond to that somehow, and you can measure it in the duct. Don't let them do that. It's true, what he's saying is true, but so what? Okay. Your stuff.
The worst part about it is if you need to make any adjustments, you can't.
You're stuck, yeah, that's it. Yeah. All right, so here's our fan again, and let's see what we're looking at this. We got static pressure. We're talking about that. CFM's down there. That was a surprise slide. Okay. All right, now we're looking at the what we call the brake horse. That's the horsepower at the shaft. That's what those lines are. Not the same as the air horse, but just so you know, that's the power that you have to have turning the shaft. And now let's see here. There's the RPM. These, you'll see later, these curves are very similar to pump curves, and the problems that fans have are similar to pumps, just because we're working with a different fluid. The thing that's really a bigger problem with one is, actually pumps have the same kind of problem. You back them here and weird things start going on too. They have a similar thing going on. So there's the RPM, and you notice on this curve we have the maximum for the classes. There's the max for class 1, there's the max for class 2. All right, this is what we call the surge curve. Do not select left of this. I mean, how plain can you get? And yet you'll have manufacturers, reps selecting it like that, submitting it with the selection on that side of the curve, and expecting you to accept it.
Is there a reason for that, or just somebody experienced in what they're doing? Is there another motivation behind that?
Costs more money for a bigger horsepower motor.
They'd had to go up to a bigger horsepower motor. They'd have had to go up to a bigger fan.
A lot of these prepackaged units are coming now. You can't necessarily adjust the size of the motor without increasing the carriage of the motor and all kinds of.
It's a mess, yeah.
It's a nightmare.
Yeah.
Trying to get NEMA premium efficiency motors into some of the new package units.
Yeah. Yeah. Yeah, and I've been following the motor development for a while too. And that's a whole nother story. So, okay, so we have the brake horsepower, the fan RPM, surge curve, and the fan efficiency is not always shown. It's nice when they do it like that. Often what they'll do is if they don't have those plotted on there, they'll have some other way of letting you know. They'll have sometimes efficiency curves plotted with a different range over here for efficiency. But this, I like seeing like this. It's really handy, as you can see immediately what you're doing. All right, so let's see here. Go through the surge curve, pressure classes. That's the thing we talked about there. Here's his equipment schedule, and you guys have that on your manual there that you can look at. It's a little fuzzy here, but typically we'd have one of these things, and that's got on there. That's basically our schedule data. Yeah, we're a little fuzzy here, but yeah. But you can see right there, we have an air handling unit up there, and I would think we have the fan data is right. Let's see here. I have to confess, I hear it. There's supply of return fan sound requirements. Okay. But anyway, you'll see something like that, and that's where most of the stuff comes from. If the guy asks for a specific class, that will be on here too. Otherwise, the vendor will choose the class, unless it's also unless it's addressed in the spec. So if it's not in the spec or on here, you're almost stuck with arguing with the vendor about the class of the wheel. If you think that you have a strong suspicion that on this job you're going to have to increase fan speed. Okay, here we go. This is a little better. Try to remember. All right, here we go. That's the type of unit. This is a VAV fan application. CFM is 18,000. Entering the external pressure, that's the pressure outside of the unit. If we put taps on the outside of the unit on the intake side and on the discharge side, the difference across the unit is 2.75 inches. Total is 5.5. So in this particular case, over about half of our loss is just inside the unit. Heads up, this is a good thing to have on schedules, because one of the things that often happens is a lot of manufacturers are not very careful about the way that they install their fans. We had a situation in which every fan was about, when we did our tap stuff and looked at the fan curves, the fan was shy about ½ an inch. And we got to make some measurements and discovered that some places we couldn't get to, which is supposed to be inlet, it was pinched. And so that we had non-uniform conditions coming into the fan and excessive pressure drop right at the inlet of the fan. So units vary, and this is one of the things you want to watch for, because you like your drops to be only the ones that are major, like coils, filters, stuff like that. You really don't want the manufacturer screwing you over on the fact that you put in a fan wheel in a not good way. There's some limits in terms of what you can do to actually fight that, but it affects your horsepower can. All right, so looking at our curves here, 18,000 CFM, and we're looking at there was 5.75 inches, or 5.5, I think it was. And yeah, it was. There we go. There's our intersection, and we can see we're kind of close to the curve, but not too bad. We're down at least on that part of this curve right here, 1073. So 1073 is not a bad selection. If we went to this one over here, you can see that if we slowed that one down, well, it's just not a good match. So our best match happens to be this one. Lost it right here. Oh wait, we're in trouble. Yeah, it has to be in here. We have to adjust the speed. So it's this wheel, and we have to adjust the speed. Wait, I'm sorry. I keep doing this on the pumps. Yeah, we have the same thing. So here's our speed. It's going to be between 1,200 and 1073. And if you light anyway, so that's what's going to be. Right there.
Question.
Okay, so the horsepower for this thing.
You got a question?
What's that?
You got a question?
So with that intersection there, you selected the one that's a little bit higher than
You said you adjust the speed now.
Well, actually, my mistake, these are actually the speed 450, 550, 650, 1070, 312. So what they're gonna have to do, if it came shivved for 1073 RPM, they're gonna have to shiv it for, let's see, we're right here at 1070. That's about the way. You know, our 20 horse went from type 1. And the 20 horse motor, we're in trouble. They have to go up to the next motor speed, our motor. So, anyway, that's what he's saying is, okay, that's really what governs there is the, I think, do we require our fans? Let's see here, the 1200 RPM. Yeah. So we're in between the two, we're gonna have to shiv it, and the motor's gonna have to be big enough to carry the load now. And that might, sometimes it affects wiring, always affects some of the other electrical components. All right. Whoops. Back to our, there's our nameplate, we got our volts, amps. Right there, volts, amps. That's down there. RPM, this is a motor RPM, not the fan. And horsepower, so somewhere here, right there, 1/2. Efficiency. And let's see, do we have efficiency? Right, should be under somewhere. Did you see it? Don't see it. Those are
74%, right?
Yeah, efficiency 74.
74, okay. All right. Yeah, so that's a small motor, and we used to, I don't know what the efficiencies are now. That used to be pretty common. So we got through the fans, duct system. Okay.
That, never mind.
Okay. All right, so we see there's an awful lot of stuff that goes out in the ductwork that affects our pressure drops. Things like this, like that, and that. All kinds of stuff out there. It's also some things can happen if you don't watch. I've had guys install things in such a way that the takeoffs for the branches would not deliver air because of some of the disturbances right upstream from them. And so, like I said, a lot of stuff can happen out in the ductwork. There are standards, sheet metal, SMACNA, Sheet Metal and Construction Contractors National Association. You can get that on the Whole Building Design Guide. You can download some of their stuff, really handy stuff. The duct standards tell you about how things are supposed to be made. And so if you're doing QA stuff and you want to see if it's right, that's a good source. And here are the standards. And how many have access to the Whole Building Design Guide? Okay. And those of you that don't know, which report are you guys with? Actually, I do have it. You do? Okay. Yeah, that's got a really good source for most of the stuff we need to have.
Yeah, we don't have access because we don't have we can get to the design guide, but we can't get to a lot of the standards because they're Corps of Engineers access only. So I have to take notes over the Corps.
So you got, that's a good plan, really good plan. Yeah.
Mechanical QB course is a good one too.
Yeah, that is. Yeah.
Well, it's a subscription they can subscribe to.
What's that?
If their office uses it enough, it's just a private service that you subscribe to.
Yeah, and some of our organizations, doing anything is, I'm still waiting for software that I waited for like a year and a half ago. And,
But IT will never let you install it.
well, that's the other part of it. If we ever get it, it probably will never get on. So, and it's been cleared for, I don't know, like 10 or 15 years. It's had its security stuff. But, all right, so static, here's the duct pressure classes, 1/2 inch through 10 inch water gauge. And then there's the corresponding operating pressure. And then you'll notice that some of these aren't rated for negative pressure. That's sort of, all right, and here's the way, we have a fan here, a duct system, and on drawings, if they're going to, what SMAC wants to see. On this side, we have a 4-inch class, that is a 3-inch class. That goes all the way to that place where it stops and becomes 2-inch, and then it goes on to where it becomes 1-inch. As a designer for the systems that we use, which are generally kind of small and pretty simple, I usually only use one class, and it's usually, I just use one class for the whole thing, and put down in a note what the duct class is going to be. But that's the two things you'll see. It'll either be noted or it'll be symbols like that. And those are the standard symbols. And that's what SMACNA guys like to see. And then we have the duct sizing methods, equal friction, static regain, and room air distribution with the devices and the expectations we have. Static regain is required, and the ultimate is an economic study. And I haven't had time to do any really digging on it, but my experience as a designer is that when you're finished with static regain, you haven't gained anything. The option of static regain or the pressure drop kind applies only to the supply side, and it reduces velocity and increases static pressure to offset friction losses in the succeeding duct sections. And I'm not going to go into my criticisms of the method, but there are legion. And it's easy to balance, self-balancing, and I'll believe that whenever in my life I see one that does. If you guys have seen one, let me know, send me an email, anything, when you see a self-balancing one that was regained. So here's a little bit about pressure drop calculations. There's round duct, square duct, and rectangular duct. So we've got 1,500 CFM, or 100 feet of length, and these are our areas. Everyone gives us 144 square inches. So we can see that the pressure drop is for the round 0.25, for the square 0.03, and for the other one 0.4. And what they're trying to tell us here is that really for duct layout, it's really best to use round. In real life, round is kind of like cool, but kind of like you have to have real good agreements with the architect for the ceiling space and a lot of other things. So generally, what you'll either see is the square or the rectangular. And typically, you won't see anybody getting out of a ratio of 1 to 3. This is 1 to 4. And the reason is because if you are concerned about space, when you start going beyond that, you have to do so much to reinforce the duct that you start losing what you're trying to gain. So you won't see that go out that much. But you will see some 1 to 4s, but not a lot of that.
Makes noise too when you do that. Right?
When you start doing too much, well, the other thing is too, they have to put in duct reinforcement that passes through the duct. And that, that gets to be a problem too. So at any rate, ideal is round, rare that you can actually use it. And when it comes down to it, when you're all said and done, your duct pressure drop is not going to be what drives your project. And that's just so you know what the difference is. Registers and grills, those are usually return air, can be to a duct or a plenum. The register has got adjustable blades, and the grill has fixed. Diffusers distribute the air into the space, and one of my least favorite in the entire universe is those. You see them a lot because right now they're cheap, but I expect they're used to drop off because they just don't perform well, especially with VAV systems. This right here used to be real popular. I like them because they allow you to do a lot with directing the air and getting the momentum where you need it, but that's a design course. Whatever we get on the job is whatever we got. Okay, so here we have air coming into a room. You notice that the area of the jet we have airflow that may not be really intuitive here, but you'll notice that we have air coming down the wall. We try to design so we sweep the wall a bit, and then we have air that circulates back up. So we generally have a circulation. We might have a couple of cells of that. Sometimes there's a three thing, like we have the cubicles. You have air going across the cubicles like this, air in the cubicles like that. All right, but we're trying, that's part of the design thing and part of why we pay the engineer to choose the diffusers that should be selected for the job. Something that can happen is stagnation, where we have the hot air above, the cool air below, and that's particularly true in a heated room. We try to limit temperature differences of the incoming air. Typically, we'll try to keep the incoming air in the neighborhood of 95 to 100, maybe 110 max, because the density differences get so high that you'll have stratification. Consideration for performance, we're looking on the diffusers, grills, air pressure loss, noise, the throw patterns, and we don't do anything with those in tab. I was surprised because I'm filling out, I'm doing my design, I'm showing where the air is supposed to go, and on this happened to be on where I had diffusers that have or had adjustable patterns, and I got to discover ain't nobody doing anything with those. They're blasting straight down. So at any rate, that's something that during tab, as a QC person or QA person, you can notice if the air is going in the directions that the designer showed, and if not, the tab guy can turn the diffusers or turn the grills a little large. That has to happen during tab because it will affect the readings, because that changes the resistance of the outlet. Throw distance is from the grill, and then you can measure different velocities. We don't do that except in special cases. We'll measure the velocities at different levels in the building. Not typical. Registers and grills, they have an air pressure loss and noise. Something to watch on return air. Well, all of them. You don't do it. I think we have a slide about that. You don't want them to make the adjustment in the diffuser or grill. And the reasons are legion, but two of them are it generates excess noise right there in your room. And they have a tendency to leak really badly. And they have a tendency to drift. None of those are what we call good. Okay, I just said that. Couldn't have a better slide if I made it myself. All right, and constant volume systems, airflow rate is held constant, temperature is changed. And then there's the variable volume type where the airflow rate is varied and the temperature of the air is constant. And we're seeing a lot, probably the majority of what we do is variable airflow. And that's the variable volume one. Okay, what kinds do we have? We don't see many of those anymore, although I hear they're coming back. We're going to see it. That has a fan section, hot, cold deck, we'll call hot deck, cold deck. We mix air coming off of each of these, coming into a duct that goes outside. And in real life, in a military facility, one of these is going to be dead. During the winter time, if we're heating, the cold side is dead, and the hot side is on, and we mix the outside air and return air to get the air temperature down here, and then we provide whatever heating we need for the space with that other damper. There's another version of that, but basically they mix two streams of air to get the air temperature in the discharge what you want it to be. Okay, so here we have one. We got several zones coming off this air handling unit, and for the designer, the key thing is that all these pressure drops out the diffusers has to be the same. Otherwise, it's almost impossible to get it to come out and get it right. So we've got temperatures that control the dampers. Oh, there we go. They'll do that. Here's what it looks like physically. These are the ducts are coming off this way. And so here's the one deck, and there's so we have the hot deck, cold deck, and those are the. So when that's closed, that one's full open. When that one's full open, or when that one's full closed, this one's full open. They modulate 90 degrees. They modulate in opposition to each other. Okay, we also have a single duct for terminal reheat. Okay, so what we've done on that very end one, we have a heating coil in there, and everybody's getting the same temperature air, it's constant volume, but somebody needs more heat, zone 5, and so you can modulate the coil to heat it. So constant volume systems, we have multi-zone, single duct with terminal reheat, and dual duct. Okay, so this is what they call dual duct constant volume. What they actually do is it's kind of like two VAV systems and that are together. So we have a slight supply duct and warm supply, cold supply come together in a terminal type, and they mix the two to get the output that you need. That's generally only used where you're trying to have real tight controls on temperature and or sometimes humidity. And usually temperature though. I have seen them only one application in my entire life, and they converted the whole thing to VAV while I was around them. In fact, I was involved in the conversion. It was exciting. We have now we have VAV and basically single duct VAV, and here's what we look like. Okay, the temperature sensor talks directly back to the VAV terminal. And we have a static pressure sensor out there that determines if we're too low or not. So here we go. Supplier duct, we use a damper to change the amount of air coming into the box. And we have a controller that tells us what to do based on what's going on in the room. There's your temperature sensor. And it's got a minimum setting and a maximum. So things to keep in mind that the thermostat senses room temperature, sends the signal back to the VAV terminal controller, and then the airflow is dependent on the duct pressure. Well, this is for the dependent VAVs. The actual delivery depends upon the duct pressure. Its performance depends upon the assumption that the duct system performs like it's supposed to, which you always hope. Requires that the pressure differential across the box is essentially constant, which in actual operation is not. Generally doesn't work well because duct pressure varies depending upon the system airflow. And so we strongly recommend it for, I don't know if even allow the use of pressure dependent turbines anymore. When I started, we did. And yeah, they're controllable, but you have to learn to allow them to get along with them. So that's what it's like. You just see we have air comes in there, there's a damper, air goes out, and the space sensor senses temperature and tries to modulate the damper to match what's needed. If we had a velocity sensor, now we can control velocity, and if we know how much at any load that the space needs, all we have to do now is control, I say all. What we do now is we control the velocity. So it doesn't make any difference what the pressure is out here, what the pressure difference across the box is. This thing is going to be changed in order to maintain a velocity there. So we get temperature back here. It tells us what we need for heating or cooling. That uses that information to determine what velocity should be seen here. And now you can have pressure changes all over, and this thing will change in order to keep that velocity what it's supposed to be for that condition. That's pressure independent. So the advantages are, I just mentioned you don't have to have a constant pressure. It's got the airflow sensor. The airflow set point is adjusted by the room thermostat, and it's maintained by the VAV damper. And the airflow is independent of duct pressure until you get down to the place where there's insufficient duct pressure, but that's another problem. The VAV box knows how much air is being delivered because of the velocity sensor. Now, right here I need to mention something, and that is that during tab, you need to check to be sure that that box knows what the duct dimensions are. Because very often the control guy will go through and he'll put in all the same size for everything. And this actually measures CFM into the system. Don't know why they do that, but they do. I guess because they're reading the need or something, but at any rate, so instead of being truly, we just look at the velocity of the room, it actually looks at cubic feet per minute into the room because it multiplies that velocity to put, just like we did by hand a while ago. And so that will always be wrong and it'll cause you problems. So be sure that your tab guy checks to be sure that when he calibrates that terminal, that terminal also has the right area associated with it. the right duct dimensions. And he'll have to talk to the control guys too for that, but it is really key. I found out about that when we discovered things wouldn't work, and then we went back, so that's what it was.
So it's not set by the manufacturer and.
Well, no, because the manufacturer doesn't know what duct you're putting it on. And if it was, you'd still have to check it.
That isn't part of the VAV box and the terminal flow sensors in the box.
Well, sensors in the box, but he doesn't know what you're up to. And even if it did, it'd still be wrong because it came from the factory. No offense.
Yeah.
But has anybody got any factory stories?
If you got a 8-inch VAV, it's 8-inch.
I'm going to say yeah. The other thing too is that they come from the factory, and the controllers aren't necessarily provided by the factory that puts them on. So if I buy a Train VAV terminal, it may have a Honeywell controller. So Train is not going to do anything with the Honeywell controller. So that's part of the problem too.
Even if it were the same vendor, that duct size would have to get input at the job site. Because you're just getting a off-the-shelf VAV controller that has to get configured for whatever size VAV you're putting it into. Does that answer your question?
Yeah.
Yeah, and very often the control guy is in a hurry. Don't know how to say that nicely, but he's in a hurry. Okay, let's see here. One of the problems we have now is the belief that if a room is empty, and this is a philosophical thing, so I won't dive into it too much, we have a minimum airflow. And very often that minimum airflow isn't effective when the room is totally empty and all the lights are off and the equipment's shut down. And when that is true, we can subcool the room and we have no cooling. And so in that case, we very often have to put in reheat, because reheat is better than cheese. Why did I say cheese? Because M is a word that we don't use on the construction site. I got corrected one time by a technician that came out while we were looking for something that had to do with the M word in walls and stuff. And they pointed out the fact that they were right. You never, never, never use the M word on a construction site. Make it a habit. It's cheese. My, it's a bit cheesy in here. Okay. The M word we stay away from. You get a panicked customer, you got a problem. Okay. So a little bit about clean living and clean talking. Cheese. So there's the cooling only VAV box. And just find out how I did that. And it's got a single duct. It's pressure dependent or pressure independent. It's got this one's got reheat. Okay, where's our reheat? There it is. Heating coil. Usually it's not always, but usually it's separated from the terminal. It can be built right into the end. And there's our controls for the heating coil. There's VAV reheat. And let's see here. That was the electric one. And let's see here. The key thing is that the user knows that the boiler has got to run all the time. So basic settings, we've talked about the size of the duct. Airflows have to be set, temperature set points. All that happens during the tab guy's calibration. He'll set the max and mins on it and check them. The configuration software setup, again, is used during that time. And setting heating and cooling set points, all that kind of stuff, again, gets put in by the, this is a cooperative thing between the tab guy and the controls guy, but we have to get the controls, electronic controls of what the real input is. Here's a VAV terminal that has a, here you guys. This is a series type. That fan runs all the time. And when you balance it, you want to be sure that when at full airflow here, you have just the tiniest to do with a piece of TP. Just a tiny bit of air flowing into there. Tiny, tiny, tiny. Or it affects the cooling. But the cool air comes through there, goes through the fan, and into your your duct system. That comes through the return air plenum, and typically you'll have a filter there. And then, so that's the series, now here's that's the series, that's typically how they look. And they have a constant airflow of the system all the time. And they may or may not have a reheat coil. In the unoccupied mode, heating, if the space gets cold, the fan can run without starting the main air handling unit. And you can use warm return air for heat. So you got the setting, high, low, medium. Temperature set points. Are for cooling, heating, occupied, unoccupied. That's usually not that's in the control system. And the calibration of the flow sensor is required by the tab guy. So that's a key thing that he does out there. Here's one that I like to see a little bit better because the fan's out of the airstream. The one I like even better than that. The heating coil is there by the fan, but that's another story. But this is another one. That fan runs when it's necessary and doesn't when it's not. And when it's required to heat, the fan will bring in air from the airplane essentially, as you see there, and will run up through the heating coil. You may or may not have that damper open there. Those are really good for, like the others, for night setback. And there's backdraft damper. Better have motorized ones. And there it is, the this one right here. Well, this right here, you can see the fan a little better. And I think you can't see the fan too well on the other. So the plan is parallel with the primary air connection to the box, and the air that's delivered is variable. The box fan runs only during the call for heat, and it may have a reheat coil. They just use plenum heat. Occupied, unoccupied mode of heating if the space gets cold, and the fan, you never have to worry about it starting the main air handling unit. It'll run, it won't start out going backwards, and uses warm return air for feed. Temperature set points. That's we've already talked about those. And okay, so single duct, we got pressure dependent, pressure independent, preheat. We have the series fan powered or the parallel fan powered, and that's the variations we have on those. The dual duct you just hardly ever see. We're just putting it there because you still run into a little bit, and it'll be mostly on existing stuff. Okay. I think we've described those. We've identified, whoops, what happened to us there? Identified the major components. There's our famous picture. And okay, we've gone through the fan curve, major components of the systems, fan curve, the operating point, we talked about that. What we want to miss, there's a typical fan curve. And I think we pretty much rolled those horses into the sunset. And I think that's pretty much it. And probably no one's going to ask any questions because I'm like running late. But if you want to, feel free to, after you come back, or sometime you can corner me or talk to somebody. But it is now chow time.
I got 12:10, let's leave it back at 1:10. I don't think I'm going to go anywhere, so if y'all want to leave your laptops, feel free. I'm going to stay here.
Yeah, I'm going to be here too, so.
So run the rest of the cafeteria.
Why try that?
I'm not exactly, kind of sure kind of guys, so you have different opinions, but I love it pretty much.
You still moving up yet?
Yeah, I think I've done that shit. I'm kind of counting on, yeah, so. Pick up the load and do this shit.
Okay.
I think it's really two of us.
You're pretty much there then.
Yeah, yeah.
Okay. All right. You need
But,
something.
thanks for checking here, yeah.
I'll be, checking back closer toward the end of the day.
Okay.
All right.
I still got a VPN.
Somewhere,
Here's. Actually, I normally hit here and in my drop down that says VPN. It's just the way to connect it. And then, but you don't have a name for it?
Like, cause it's like saying before, see what I hit.
Yeah, the only mine is either eastern or western. And then,
Oh, yeah.
yeah.
Yeah, I'm here somewhere. I remember it's one of these.
Look for the one that says Cisco Key today. This thing,
And this one.
yeah. Yeah, because mine, as soon as, I do this citrus, or Cisco Connect, it brings mine up either, you choose eastern
Eastern
or
and
western.
western, right. I remember that.
Yeah. Like I said, ethics training, I got a message from our district, he called it, he's like, where are you at? I'm like, boss, I'm in Big City, knowing where you just said. He's like, what? What do you mean I said you? I said HVAC test and analysis. I said, oh, yeah, that's right. Just get your ethics training done for me.
I'm all year.
So you know,
Okay.
You can fill it up right on back.
oh,
There you go with it. You remember, I'm trying to get my email.
okay.
You know, the weekend. I usually bring my laptop out of the office. So we're going to, this one, and this one.
But it doesn't give you the option for the eastern or western.
Are you on the,
That's what I would,
This. Yeah. now it'll be, yeah, it should give you now, if you now said right, that. There you go. Thank you. So you hadn't even made it to the first step of getting to the internet.
Right, if you wanted that for VPN to be.
Okay, Eastern. Became a long line. The only difference between Eastern and Western is sometimes Eastern will keep logging you on. Sometimes they will go to Western, and then sometimes it's vice versa.
Yeah, I remember.
We bounce between them.
Thank you. All right.
Well, you can also turn your speaker down too, on that also. Sure.
And then I just send you, my address, right? You said.
Correct.
Then, okay.
Yep. Thank you.
Okay.
Sir.
Then one night, you were teaching thinking 108, 21, which is only 2/100ths on the second, or the chapter, and
Yeah.
2/100ths.
Yeah.
My niece got gold medal in one by 2/100ths. Four races in the bobsled.
Oh,
She
man.
got silver medal the last Olympics. Both, and one whereas silver and one whereas bronze. And she, both the Olympics that she lost the gold was .02. Wow.
Oh, man.
And that's four races. And the race for like 80 miles an hour, like, say like 105 a minute, 1 minute, 5 seconds. So four races combined, she missed the gold by.
Oh, good job,
Yeah, yeah.
man.
We had a good time watching her. She's still training now. She's gonna try the next one, but she's getting up there in age. She's 31. So, but we were all excited. Yeah.
That is
It was good no matter what. I mean,
Yeah.
Quick, you live around here? Or know where you're from?
Live in Oklahoma City area.
Oh,
Near a Tinker.
okay. Friend just moved out from Philadelphia, Jersey.
Yeah.
Oklahoma was welcome. Got out there and he broke up, he had to fly home.
Oh.
That was like 3 days. In 3 days.
Well, I guess, you get to know each other on it.
Yeah. He wasn't happy. He almost sounded like he was all hurt, you know, but he was like, usually I was happy.
Yeah.
He was friends one. He looked like my neighbor. I gotta take a picture of me. He was I mean, you laugh and talk like that, you know, but, there's a guy that works with me today. He can do it, he's 56. I want him to work for us. But he's 44 years in 5, 6 years in Philadelphia as an inspector. Well, the first year had. He didn't get that fully, so knowledgeable in UKT. That's why I hired him. Because I didn't know you had. They did pass, you know, to the agency. So we stuck him on a $22 million art building on reserve center. And he went and started looking at everything, calculating everything. Well, he calculated the water gauge, and it came up like 3.8 and 4. And the contractor said that they're going to basically stop work on something like a lower water gauge, because you can't. If you go try to, if you can volume of the thing and with that pushing, you'll have problems. He all this up. And it's almost like he's pulling his own hair and causing more work for himself because they already do his job. The whole building, now they don't want to throw it away, so they're arguing, you know, well, and then he's like, well, according to SmackDown. And I told him, we don't care about SmackDown, we don't care about code. It's whatever's in the state, so he's like, caught, like, he's doing the right thing, you know, he's doing a great job with QA, better than I would ever do on HVAC. But see what I mean? And now it got to a point, and it isn't just the HVAC, this whole building seems like a disaster. Now, they're micromanaging him because the problem's all with the building, like the steel guy got fired, roofing guy wasn't doing his job, everything. I mean, the windows aren't even in the building, they're already sheetrock in it, the roof's not sealed in tight, it's clean in there, there's water all over. Yeah. And it's just like, and I'm sitting next to him, and every day I hear something new, like a new problem. I mean, you name it, this building, it's just crazy. But like I said, he knows all this stuff so well, and he took the time, and he took the, all the paper, stating the work, and he looked at it all and figured it all out. He's like, they're not doing the right thing.
But yeah, you do, you run into more trouble doing that, sometimes you just sit back and let them fail.
He should be, I told him, I said, listen, you should have just reported it and moved on, right? Here's the efficiency I found. You let somebody else down about Paul Johnson era.
Yes, and went to Georgia Southern when he was there for that championship.
Oh, okay.
So, yeah, I was.
So you can't get rid of him.
Yeah, he came back.
You push him?
Yeah.
Or do you just say, hey,
It's definitely love, hate there. Like, I was a supporter until about 3 years ago, and then obviously that, even this year,
tell somebody
it's probably gonna be bad.
you know, 8,000 for that. Doing it
I don't know, I think they need to
for
give out
44 years. Knows what you're all about. But a lot of times they.
Well, it comes down to the
I'm curious to
contract,
see
what's in
how they handle it.
Yeah, it's
It'll take a while.
Yes.
I'll pray that.
Oh, that's a problem.
Yeah.
We have that problem all the time. buildings.
Oh, I'd love to see it. Oh, goodness.
I'm always.
Yeah, they're having a rough one.
actually got accepted.
I don't even know about all that. I know.
Yeah, I started out, I had no intentions on going there. I started out going to show.
Put in their alternative.
Sweetheart.
The network.
Right.
Yeah, water.
Yeah, no, it worked out for them.
Plumber didn't put nothing in, and he brought it out.
I'm really curious to see if they hire Johnson.
It's like 10 or 11.
Our assistant isn't
And we're,
I'm hoping for,
he's catching things, but.
nice. I haven't even looked at the all going where, who's been interviewed.
We got something out there.
Well, I heard. I'd be curious to see if any of them are interested. I hope so. But, that doing a couple of scenes, that gets you a little where with the options. I'm really curious. If you try to get some other scheme, we're just, we'll see. Yeah.
It's the contract is a lawyer. This guy is a lawyer, and he's doing work for the day. You look at that too.
Yeah.
What can do away with? How to do away with?
The best team. On our side,
Destroyed exactly that. We have a park that's a year old.
We got Clemson.
But it's ground water, resource,
Really, that's
not a whole system. It's called artificial system.
The thermal.
But it, the design is groundwater is always 55 degrees, and that's not actually. Water, groundwater.
You know, see it, maybe on occasion, Mississippi's
Cold, yes, too cold. You'll trip out the heat unit all the time. You'll trip out. You get nice setbacks. Start up.
I'm actually in grad school at all.
Energy.
Are you really?
Puts it out.
At all, distance.
So what's their?
Okay.
Yeah.
Yeah, they got
You're required by AFCA to do nice setbacks. But even if you run it 24/7, it just doesn't have.
Yes. Construction management. I was in University of Maryland on protection engineering.
I knew they had a lot.
I just couldn't keep up, so I dropped it.
You got a contract.
That's too much.
Well, like this, you know, and that's all was crap. But listen, there's one job in our spot, he fired the steel guy, and he was putting stuff up, he wasn't squaring the front yet, then you got a whole building up there, and then you got to you shorter than he was, then tore off in 3/8.
Started off.
I was gonna do this site here, and you can't do it.
I don't care what causes the fire to start. I need to know how to put it out. That's right. I don't care about chemicals.
Or the pump.
All right, take care.
So, okay, now how do you fix it? Now you're tapping the decking down.
Right.
I mean, I mean, they're different walls, and they're like, oh, we'll fix it. How you gonna fix it?
Yeah.
And then they connected the Jura rock on the inside, you know, because it's, you know, they, instead of fiber, they use Jura rock, which is good, but it's all screwed on. Now you can't get the wave out of there, because you have to take the sheathing off, straight, and then put the sheathing back. The sheathing helps keep it straight.
Right.
It's like, I don't know, it's just like, it's a little crazy. I'm like I said, I'm happy I didn't get on it.
Well, on that self-inflicted, because we hired a little bit. Too.
Yeah, like, even when I was a bit of site contractor for 25 years, I hated a little bit. He told me it's a little bit, I said, I don't want to bid on it. But I'm not gonna be a little bit,
Right.
because I'm not, you know, I'm gonna give you quality stuff, you know, and a lot of times when it's a little bit, like on the government, they stipulate what you want, and what they call for, what they ask for. We deal with contractors now, they're like, we're doing negotiated job instead of bidding. Then they come back and like, well, that's not what we negotiated on. Well, we're not privy to all the negotiations. We should have it, right? The project engineering 2A, but we don't get it in time. They're like, well, that's not the way it's supposed to be. You can't do that. Well, that's not what we negotiated. So then they go back and like, sure enough, it wasn't negotiated. And I'm thinking like, yeah, but if it's wrong, who cares if it was negotiated that way? Let's do it right now.
Right.
Not, oh, you could do it wrong because of it. No, then you run into that. And then they're like, well, we only had 5 days to negotiate because they want to hurry up and get it awarded before the fiscal year. So they always seem like here, since I've been here, hurry up and get all. And it's siding renovations. We're residing the hangar at Lakewood. And they're like, well, we did. And I'm thinking like, on every job on everything, it says field verified. You got to look at the job. You can't just do the job on paper. They didn't know, they were saying they didn't know mechanical work because the drawing was done 20 years ago. Yeah, but you went to that building, you've seen mechanical room attached, it's been attached for 15 years, it's been there. You can't get siding off behind it because it's attached. Then your correct thing was send RFI and say, what do you want us to do? And then let the government tell you, and the government said, take it out. And then the roof has come in, but that wasn't still work. Okay, so you'll get that. You'll get money back to bring in a roof in because that's extra work. But everything that they would take off, you do that mechanical room zero. You look at the job, $3 million job. If I did a $3 million job, I would have went there 20 times. I looked at my paperwork 20 times. By the time I put the bid in or depreciation, I don't have to look at any paperwork. I know what I'm doing. You know what I mean? Because you went through all the steps. So, yeah, so it's funny what we deal with.
Yeah, one of the guys that taught the ASHRAE course that I did a month ago or so, very knowledgeable mechanical engineer. It works, you know, throughout the industry, very, very, various different capacities, knows what he's doing. He said if it's low bid, there's my price. And Spectra Systems that works.
Yeah.
You won't have these failed building problems and all this stuff. I know what I'm doing. Here's my price.
Mm-hmm.
Government doesn't get people. Must go,
No, no. Yeah, because I'm surprised that John, his name's John, I'm surprised he caught all that. But that's his expertise is his HVAC. That's all he's done his whole life. He was in a union, and he did design and build for engineer firms, he did design and build for union, and then he went on the sector, and he really should be retired.
Yeah.
I'm not too sure why he's not. I think he's trying to max out his TSPs, and he's doing 5 years for who is benefits? No, benefits with the union, right?
We had a guy that retired from the state, and the federal for 6 years.
Yeah, that's
He had done medical. This federal has better medical.
I think that was it. Because he said, I'm going to fly. You know, remember last year, he changed it to 10, I'm like 66. And his wife said, she's like, after about 5 months, he talks about how at home, he's like, oh, because of that job. Yeah. I'm only doing one job. Yeah. They set the countdown for 30 days. Out of the steel thing, nobody worked. Nobody.
Right, yeah.
Now, you know, he's a lawyer. He's going to come back and say, well, I'm behind because you shut me down for a month. You know that's going to be one of the arguments.
Right.
And he might get more out of it. You know, because I know a lot of times, it seems like everybody's always worried about suing. Even when I went and applied for a government job, they sent me the, you know, if I was going to accept the job, and I signed it all, and then I went in, and they said, you know, are you a veteran? I said, yeah. Well, I spent 2 years in the military. I went in for 2 years. Well, you got to be 3 to get veterans, for veterans, you got to be 3. I was like, that's baloney. I was in for 2. And then I was 4 years in after, that's 6 total. But I did that in separate. So they told me, because somebody might come behind you and say, well, he's not a vet. So they're worried about some fictitious, crazy green person or someone that might. So then we did the whole, and we did the whole one. You know, oh, are you a licensed contractor? Well, I am. So that was a, you know, what will happen.
Here's a funny one today. Yeah, because the all guy get ready to go. They want to start.
I back you time. The bathroom building.
Retired.
Yeah.
Okay, sounds good to me. Yeah, we got a turn around. Yeah, they're children. Things are, you're not familiar about to buy back the time.
Yep.
Come out. Guys, here, go. No, she's like, it's big. She's like, are you retired from the military?
Yeah.
You used up your. I'm like, oh. They left that. Yeah, I had. It was before my time.
The worst HR department.
Yeah, I had to let it lunch.
The reason right now, RBA, we're stuck on it. Right.
I never was why, that's why I started, but yeah.
Oh, okay.
But that's
I'm watching.
I'm trying.
You would want to check. I don't know.
Well, not really.
It's still worth it. You would be. I've already started. It's two, that's where, so I'm ready to. I want to know. So, yeah, that's what you're talking about. That's all the same place. Yeah. Well. I was looking for it, but it goes to HR. Well, first, and then they show that. So you're contact. They got a good lot of problems. She just. All the players now. I like the vision. I don't want to see what
And I'm not a big fan. They do what they do. I really feel like I had a good brand. And I've got, there's a police ongoing training. They're really simple. And it's cool. Your face is kind of trying to. Terminology. They Brother Sterling called May. I don't know about the other. I think that's one number. What did they use?
There's no May on both of them. There's only May on both half of it.
Yeah.
I was. Right now, they're both there. They say you can bring us. We've got all three. So my project is the last one. And they even made me do the contract. They did not want to have, because if they started with it's still registered to the appropriate user. And they didn't want to have any paper lease. Not to say that they were doing ground gas, but
well, that was just like a tablet we used to use. A resume's not supposed to be a template, it's supposed to be your individual qualification.
well, we're kind of down to the future.
So this is like, you just sit there. I didn't report.
So I'm glad to hear that your system ended up. Yeah. That was my first deployment. And
I'm gonna email.
I got the look desk, yep, there it is.
Yeah.
My CID that I have. The field vaults.
Cafeteria.
I need 5 products. That's what the TCX was. Because that had, they were bringing in stuff. And I had that money.
Yes.
So, Once it was under design, did some more research.
I got it. And they're all wrong.
They were trying.
Yeah, but you know, you know, why? I said, I'm gonna get clean with it.
Oh, it's a.
I'm telling you. Yeah, I got my son out there. Oh, you can't hear it.
It's awesome. Stores and later at the, discharge.
So, you know.
No. Yeah, they should. There should be charges.
Trying to get on that. I was like a mom could.
We did this.
Years ago. Yeah.
We had a fuel fund that we.
I agree.
And worked its way around, you know.
Cool thing like this. And
I
just
think,
and, you know, she comes in the kitchen, snakes, tees up, red boots on, throw the jacket on.
I must have looked at them.
Yeah. Where'd you go?
Oh, yeah.
It was, you said my boss.
Somewhere in that range.
Like, you
Plan to fly our tanks. We did that last Oh, so they wanted to get a page where it can handle all the C5s. And get them in out for it.
What did you do?
The field on this side, they're all standing there. Next to that Russian thing in the back. Is our fault. How they give you a smartphone, gives you a stamp. They only issue us yeah, I had
And I didn't think sleep while I would be working. Take a sleep while I was fine, I'm gonna do something here. I got a 33 still, move back home. To restart for my thing. So that's the goal.
Yeah, reset.
Yeah. This time I changed the locks. Just as we will keep that, is that change that? Yeah. How doable are they? At least for a lock and a key. Yeah, I have mine. I was 6, 7 years, no problem. So they take for guys, 3 trip away, they last, still have the key, right? Oh, yeah, there's a key out outside. Yeah, okay.
So your battery's good, Daddy.
Yeah, but none of my kids have keys anymore. I'm gonna want to keep on. So up there, it's real old doors. I have a lot of multiple copies of keys for her vehicle because she'll, you got spare keys? Well, where's your keys? I don't know. Well, where did you go? I don't remember. Who were you with? I don't remember. It's been a good time. She's been great. Matter of fact, spring cleaning, and I need to do replace the windows, the back windows in the freeway. I'm like, the window, I don't have a throat. So look at it and, my goodness. Back then, how did she work place? I said, well, what did you, fly up there? No, bricks. I'm like, bricks. Brick is if you're holding it. I locked, she locked the key in the vehicle and thought that was the easiest way to get in, just break the glass out. And I was like, that was a very good idea. I said, why didn't you call me first? I just called you last week because I had lost the key, so I didn't want you upset.
But you better have to replace the window.
That's a problem. Yeah, my son don't want to do that either. Well, now you know, I just retired in 2014 Grand Cherokee. Hope had 392,674 miles. And I retired it only so I could hold the boat. And so, I replaced her with a 2001 Jeep Grand Cherokee that has 4.7 V8. And since, because I refuse to have two cars. Yeah. So, I told the guy, I bridge, get out years from your car's paid for, that I have to get a vehicle. So I called this one Bridge. So I went through, did the history, just like I did in the military. I had a 96 Grand Wagoneer, one with wood grain. Yeah. And, we loved it. They had 390. And I bought it from transmission cooler, got the depot, the transmission. And I was getting ready to take those down to the junkyard and just, sign her up. Here you go, a few $100. So they go do this. Well, don't take it. So I just put a brand new whole application system in there, and tired of it, about 700. He's like, he goes to the bank the same day, gets $700, I signed it. And, reason put the navigation system there, one of the guys at work had to, he did, I said, oh man, it was cool. And I went up on the navigation system, dropped the headliner, installed it just like it would be back to include the backup camera in the hatch. Yeah. Put it all back together, just took it to the base show there, said, look, you got no navigation. Then it's around the shoulder. Out of this, I told you, like,
Can y'all see that okay? The back?
Kind of like.
Too small. Ish.
Yeah. To operate two monitors on not next to each other is a challenge.
Yeah, but my kids graduated college, so they're living back at home, degrees.
Where's that?
What's that?
Where's that slide at?
It's not, it's just an image on the picture. Bring it on.
But problem is that, he's not, because he didn't, didn't study, we're going to do the game. Get on my midterm. Loses. Get a job. Yeah. I said, if you said, go work for next. Or you take one class at a time. And then you still cheat at home. And I said, I said, it says we don't. Yeah. Yeah, you can protect those credits. Yeah, the oldest she did, 1 year. College. And then
Yeah. Does that not do that? No. Yeah.
All right, we got a few still not back, but I got 110. Go ahead and get started. One more logistical thing tomorrow. I'm not sure what doors everybody came in this morning, but the only doors that are going to be open tomorrow are going to be this one and the one far down that way. So everybody, if you want to, you know, we can use this door, but all these other doors around the front of the building, they're going to be locked. So just these two for tomorrow. Everybody was given a copy of this manual. This is just another Gateway is a great place to have this course. By the way, they do refreshments. They give us some stuff that's not required. This isn't required. They gave you guys a copy of. This is actually an AABC technician training manual. This is a wonderful resource. This is something we don't have access to through IHS. So this is, you know, if you were an up and coming technician for an AABC company, this is what they would give them to train them with. So, you know, if you got a tab question when you get back, this is going to be really excellent. I don't even have this. A lot of the tab stuff we can't get through IHS. The AABC manual, the NEBB manual, these are things that are not on IHS. Like, you have to purchase these to get a credit card. For whatever reason, they're not on IHS. I also gave you another small reference manual. These are new. They had to give these out before. I haven't had a chance to see what all is in here, but they really gave you some great stuff in that student manual there. So we talked about a lot of pieces and parts this morning. I'm going to try to put some of those together now. We're going to try to actually measure a piece of air moving equipment and talk about what things are actually going to do. What data do we want when we're measuring that? And I'm just going to read through the objectives for this section. Be able to describe fan and fan motor performance measurements. So what pieces of data are we going to get from that, and why is it important? Be able to describe the system curve and how it relates to changes in fan performance. So we showed you a fan curve. We're going to add a system curve to that in a minute. I'll show you a slide. We're going to go over fan laws, so more math, but these are important. These actually get used out in the field by your tab technician if you've got to make an airflow change on a piece of equipment. We're going to talk about the various tools. Got a lot of examples over here of what tools you actually use to take some of these measurements. And I'm going to briefly go over the tab procedures for you, how a tab guy would actually go through and balance a building. They're abbreviated procedures. If you want the real procedures, you go back to these books and tell them exactly how to do it per their standard, and they are different per the standard that you look at. So AABC has a little bit of a difference in the way they tell you how to balance a air side system and a water side system than the way NEBB does. But we'll just kind of go over them in general terms for thought process anyways. We're going to talk about fan terms again. We showed you a slide earlier as far as the actual construction of a fan. Got to touch back on the fan curve, and like I said, add a system curve to it. The system curve is dictated by the physical characteristics of the system. Duct sizes, the number of elbows, dampers. That's how you come up with a system curve. I'll show you more of that in a minute. The operating point is the intersection of the system curve and the fan curve. So we got a fan curve. The fan is going to operate on its fan curve. It doesn't have a choice. It's dumb. It just spins at whatever speed it's spinning, and then
the physical characteristics of our system are going to dictate what airflow that fan actually puts out. We're going to talk about system effect, which is a phenomenon to have some unexpected losses in your system. This is really more for the design guys in here. They might need to consider. And for the field guys, it would be something that if you've got a fan that's not moving in much area you think it should be, you might want to take a look at system effect. Again, airside measurements, the tools used to do them, fan laws, and motor measurements. Talked about those a minute ago. So when we're talking about airflow measurements, we're generally talking about two things, pressure and flow. Air pressure we've talked about, and generally we use the inch-pound system, and we're talking about inches of water column when we talk about air pressure. And for reference, 1 PSI is equal to 27.7 inches of water column. So a pretty small number. Just our normal duct systems might operate somewhere around 1 inch, 2 inches of pressure. We're talking about a pretty low number. If you're using SI, you would be talking in pascals. I don't know anything about pascals. Please don't ask me. For airflow, we're talking about cubic feet per minute, and you kind of correlate that to water flow. That'd be kind of the equivalent to gallons per minute. And we're actually moving a cubic foot of air in 1 minute. That would be liters per second in SI units. Again, I've had one job where we actually had them published in SI units, and we went through and wrote every single dimension back in English units just so we could build it. Fan measurements. So what numbers do we actually want to get out of the fan? I'm going to shift back to another document real quick. So this is what we're looking for out of a tab contractor. We want to get some numbers for a fan. And as you see, this is just an air moving piece of equipment test sheet. This is a standard form that's in AABC. You can pull these up. I think these are online. They're standard forms. And so at the end of the day, we want to get numbers for all this data. And typically, the main thing we're talking about is cubic feet per minute. We're going to come in and fill out from our design plans. How much am I supposed to have? How much do I have? This is actually for 2 pieces of equipment. So this would be for 1 piece. This would be for another piece if I had 2 fans. And we're going to talk about all these numbers. All those numbers as we go through the rest of this lecture. But the point being, I want this thing filled out by my tab guy. I'm going to show you the things that he's supposed to do to get this filled out. Oops. Took me back. Sorry. Okay. We talked about static pressures. We showed you the pitot tube, and the static pressure is the one that is sensed by the little holes around the perimeter of it. And we're going to take those readings across various things. I want to know what my pressure drop is across certain things. So I'm going to actually see a pressure increase across my fan. If I measure the pressure on the inlet of my fan and on the outlet of my fan, I'm going to have a higher pressure on the outlet of my fan. That's that fan's job, is to generate pressure to overcome the resistance of the rest of the system, the ductwork or whatever it is attached to it. And I also want to know drop across things like filters and coils, because I'm going to compare that to whatever was submitted. If my coil is supposed to have a 1/2 inch of drop across it, I want to check that and make sure it actually is only a 1/2 inch of drop versus it might be 1 inch. And I want to go check why would I have more drop than was shown in my submittal. We talked about cubic feet per minute. We also want to measure the fan RPM, revolutions per minute. I need to know how fast that fan is spinning. On that fan curve, there were the lines that were going at a slope. I talked about the flat portion of it. I'm going to show it again in a minute. But depending on what RPM I'm going will dictate how much air I'm moving as well. And I will have a difference potentially in what my fan RPM is and what my fan motor RPM is. So if I have a direct drive fan, I may have a situation where the motor is attached directly to the fan wheel, in which in this case the fan shaft and the fan wheel would be spinning the same speed. But if I attach those two with a belt situation, I would have 2 pulleys. If they're not the same size and I have a belt wrapped around the 2 pulleys, the fan can go a different speed than the motor can. So that's why if we have a belt drive situation, and I can, that's also how I would make a change if I needed to in fans. I can change the fan pulley and change how fast the fan is spinning. That make sense? We're also going to check the electrical characteristics of the motor, amperage, voltage, frequency.
And there's a few other random things at the bottom of that report, like belt sizes and shift sizes, that also go at the bottom of the report. As I said, that fan's job is to create pressure to overcome the resistance of the duct system. We have two main types of resistances. We have friction loss, which is pretty much dictated by the amount of duct and the size of that duct. So if I have a smaller duct and I try to move more air through it, it's going to have a lot more resistance than if I tried to move that same amount of air through a bigger duct, right? And then also, as I put things in that duct, I would have dynamic losses like elbows, changes in size, tees, anything that's other than just the duct and its size would be a dynamic loss. And those two things together are my total loss I'm going to have in my system. That's the number that the designer is trying to figure out when he designs this building, is what is my total loss through my ductwork system, including any losses in my air handler as well. Important to know that pressure changes as we move through the system. I'm going to show you a chart in just a second to hopefully help make that more clear. We talked about earlier, total pressure is equal to static pressure plus velocity pressure. So static pressure was, looking at the PO2, static pressure is the one that's sensed by these little holes here. Total pressure is the one sensed by the impact tube. Okay? Static pressure due to the friction and dynamic losses in the system, velocity pressure due to air movement. So think about, standing outside, the wind blowing against you, that's your velocity pressure, right? You still have the pressure of the atmosphere pushing on you. Now you have the added pressure of the wind blowing on you. So that's kind of how I try to relate, if that makes sense, the difference in static pressure. I always have this static column of air. Just like if you're underwater, water is pushing down on you. Air is pushing down on you right now. You've got 14.7 PSI is our atmospheric pressure, probably different here. But then you add the wind to it, that's a different component of the pressure. We're going to measure those and report them. All right, so on this image, I've got a fan and I've got a piece of duct attached to it. Don't look ahead in your book, so I wanted to see if y'all can remember how to do this problem. And I'm looking at pressure on this axis and just the length of the duct on this axis. So on the inlet of my fan, I would probably measure a negative pressure, like a negative ½ an inch. That fan's job is to raise that pressure up, and if I'm looking at static pressure, I've got about 3.5 inches of static pressure. Everybody got that? So my total rise across that fan is 3.5 minus a minus half, which is 4 inches. Okay? So my fan static pressure is going to be 4 inches. We're going to use that again in a minute when we get to the fan curve. And the point of this really being that I'm going to lose pressure as I go. So friction is going to cause me to lose potential energy as I go down the duct until I'll get all the way out of the duct. Now notice the velocity pressure stays the same. There's no change in size here. So what goes into the box must come out of the box. The same airflow rate is going through the box. And if I were to measure the velocity pressure at any point, it would be the same. But I am losing static pressure. The resistance of the duct is causing me to lose potential energy. Static pressure is our potential energy. That make sense? Feel free to ask questions. By the way, this is a really long presentation. It's 3 hours. There's no really defined points. When you guys get tired, let me know. Take a break about an hour or whatever, but I don't really have any spots in here that I want to break, so time to get away from me. Let me know if we can take a break anytime. Not yet. So I can figure out airflow of a fan really 2 ways. We're going to use the fan curve in just a minute, but we learned one other way we can calculate it. So Tab Guy came in here and did a traverse. We're going to talk more about a traverse in a minute too. You're going to do one in your lab. Tab Guy came in here and took a traverse, took some readings. With 2 inches of water column was my velocity pressure. I can figure out what my velocity is from that. Anybody remember? Learned that equation this morning?
Period. Velocity.
That's going to give me my flow rate. It was this funny one, this 4,005 times the square root of the velocity pressure. Okay, so I plug in this 0.2, take the square root, and remember this was at standard conditions. This 4,005, we had to make a correction for density if we're outside of standard conditions. So knowing this velocity pressure, I can calculate my feet per minute, my velocity. And then back to the equation you mentioned, I'm gonna multiply, I was given the duct area up here, so I didn't mention that. That's the same thing as, again, we calculated that earlier, but we were given the duct area in this problem, multiply our feet per minute times our duct area to get our airflow rate, 30,000 CFM.
Do you see any instances where their PO2 measurement just gives you pressure? Because like mainly like their little box usually, like when I'm observing them, it actually puts out the feet per minute instead of the pressure.
Yes, well, for a PO2, they would have had to have input the duct size into their instrument to get that out. Like for a flow hood, it actually measures feet per minute, but because it knows its area that it's going through, it gives you CFM. I'm trying to think what other instruments there might be. As long if it has a way of knowing the duct area, yes, it will tell you cubic feet per minute. But just this too, all it's measuring is pressure.
No, I'm saying feet per minute, the velocity. It spits out velocity.
Oh no, I'm sorry.
instead of
Yeah,
the
I
pressure.
missed you. I'm sorry.
Like it calculates the velocity on its own. I'm just wondering if you've seen
Yes.
anything where it's just putting out the pressure, not the velocity.
Is this a chip?
So,
Because I don't see
You can
it.
just program a chip to do that.
right,
That's easy.
correct. Yes, as long as it's compensating for density, which all the newer stuff pretty much does. Yes. Sorry, I misunderstood you. Any other questions on this slide? Okay, back to the fan curve. For this example, we're going to imagine that this fan is operating at 1,300 revolutions per minute. So we went out there and we measured it. Talk about how we measure that in a minute. But this fan is going to operate somewhere on this curve because that's how fast it's spinning. So think back, we looked at what the pressure rise was across that fan. It was, I thought I plotted, sorry, it was 4 inches. I thought I had lines showing that, but we subtracted these two numbers, came up with 4 inches. So I can plot that. So I plot my 4 inches of static pressure on this axis. I take that over where that is intersecting with this fan curve at 1,300 revolutions per minute. I can drop that down and figure out what my flow rate is, 30,000. We came up with that same 30,000. So that's the two ways I could have figured out how to get airflow out of that piece of equipment. Hopefully you do those two things that kind of line up. That's what we were talking about earlier. They're not going to be exact. Hopefully they're close. 5%, 10%. They're going to be pretty close most of the time. If they're not, that's when you start digging deeper into it. Why don't my numbers match? So I talked earlier about the system curve. The system curve, this is dictated by the ductwork and all the fittings I talked about. Basically, there's a squared relationship. I'm going to show you that in a minute, but this is if my damper positions don't change, my system curve doesn't change. It is set. It's basically, you can equate it to one big fixed orifice. It's one set pressure loss through that system if my damper positions don't change. If I go out and close the damper, so this was our system curve for the example we gave just a second ago. If I were to go back and put a damper right here and close it, I would change my system curve. Okay, if I were to do that and I close that damper, what would happen to my airflow? My airflow would go down because I created more resistance. I was operating at 4 inches of resistance. If I created another inch of resistance over that damper, I would then be moving 28,000 CFM. That's an important concept to understand. It's called riding up the curve. My system curve would then be wherever that intersection was. I have a new system curve because I changed the physical characteristics of it. So in the same thing, I can slide down my fan curve. If I have less resistance somehow, I'm going to go down that curve and increase airflow. Make sense? Questions? Okay. This is saying in a different way what I just said. At a fixed fan RPM, the operating point moves along the fan curve as dampers open and close. That's what I just tried to explain. Shifting up and down the curve at a fixed fan RPM. So in that example I gave, my fan speed stayed the same, 1,300 RPM. and I rode up and down the fan curve by changing damper positions. Fan curve operating point cannot be predicted. You just have to plot that. You measure the pressure and you plot it on the fan curve. That's different than my system curve. The operating point moves along the curve as the RPM changes. So what I can also do is come change the RPM of my fan. So say I'm moving too much air, I can drop, if I bring the speed down to 1200 RPM, I can do that with a shift change, potentially. Or if I have a VFD on it, I can just slow it down with the VFD, right? Just change the speed. And when I do that, I'm actually going to ride down the system curve. I didn't change the system at that point. I just changed the speed that my fan was operating at. So I'm actually going to ride down the system curve at that point. I have a new fan curve. I'd be operating on this fan curve if I did that. Good? Ask questions. You two guys. All right. And guys.
I got a question. Where did you get the operating point, the number 35?
That was, I measured the static pressure of 4 inches.
Yeah.
And I knew that my fan, I gave you that it was running at 1300 RPM.
But where did you get that from?
I just said it.
Okay.
Sorry.
Right.
I probably need to add that to that slide. Yeah. So in this example, the fan's operating at 1300 RPM, and then I plotted from my measured static pressure over to whatever speed my fan was operating at. All right, so going back to one other concept here, what size fan motor would I need to accomplish this? That's not really part of this, but I want to throw that in there. My horsepower curves, these red ones,
40.
I heard 30 and 40. I would need 40. If I was operating here, I would be somewhere in between 30 and 40 horsepower. Does everybody see that? I'm in between these two at this point. Oops, sorry. A little lag in this thing. Okay, fan static pressure. We're going to report total static pressure and external static pressure. So for an air handler, for a fan, I'm only really going to have one measurement. That's if I got just a plain old exhaust fan. If I've got an air handler, I'm going to have 2 pieces of filters and whatever else I have. So my total static pressure is going to be like I did in that example. I would measure the suction of my fan and the discharge of my fan. That's the total static pressure that my fan is creating. If I were to measure the pressure on either side of my air handling unit, that would be my external static pressure. It's external to the unit. Okay, so that's, if you have an air handler scheduled on a piece of equipment, that's actually both numbers, but the total static pressure can be different for various vendors. So you're always going to see external static pressure. You might also see a total static pressure on your equipment schedules. We good with that?
That number we verify, the tab needs to verify, or is it just going to be?
So you definitely verify it in the submittal phase. And then, so you want to make sure that's going to tell you if you got a big enough fan. You're going to check that on the fan curve. And they're going to give you a fan curve as a part of their submittal and show you what my operating point is, and tell you what motor size they're giving you with it. Those are all things you check in the submittal phase. And then yes. And we'll talk about that. We're going to look at tab reports in a little more detail and check what is my actual external static pressure and what was it supposed to be. Pitot tube, I think we covered that. Does anybody want to go through pitot tube again? The actual construction of it. We got basically we're doing total pressure at the end of it, which is pointed into the ductwork, static pressure on the outside of it. One thing I guess we didn't talk about is the depth gauge markings. The tab standards tell them how many measurements they have to take and how far apart they are, and we'll go over that too. That's why it has depth gauge markings on it. Just another example of that. Okay, so pitot tube actually gets hooked up to, you would always see a digital gauge, but for demonstration purposes, I think an old manometer helps visualize it better. So if I hook up a gauge right here, and this thing's too full, it shouldn't have that much fluid in it, but if I hook up something that is generating pressure here, it's going to push this water column down. You can actually see in it. You can kind of visualize that pressure would force that water column down. And so there's different ways you can hook these up to get whichever reading you're looking for. We talked about 3 different types of pressure that we can get out of PO2, but you're always going to see this on your job site. You're actually, unless they change it, you're actually going to see these out in the lab tomorrow. But we'll talk about why we have 2 ports here in just a second. But I'd like to think that it helps you visualize the pressure actually moving that water column down. And so, depending on what I want to measure, I take my pitot tube, support the node. The tip has to go in the direction of the airflow. Okay, and if I want to measure static pressure, now this is actually, you know what? This is what I wanted to bring up. Found another chart that they gave us that I think was better than this one. Just a second. This is in one of the books that it's the same material, it's just presented a little bit different. This was in the smaller of the 2 that they gave you, page 26. So if I want to know just static pressure, that is this port. So I would measure, and this is assuming I have positive pressure. If I want to know just static pressure, that's the one going around the holes inside, I would hook this up to this side, and you can see that it would push that water column down, and I can read just my static pressure. If I want to know just my total pressure, I can hook up to this port, and it's going to move that water column down. But if I want to know my velocity pressure, which is what I want to know to determine my velocity, I can hook both of them up. So I hook up which number is going to be smaller? Which one do I hook up to the low side? Static is going to be a smaller number, because total is static plus velocity pressure. I'm going to hook up the static to the lower side. I'm going to hook up the total to the positive side, and now I'm going to see the difference in those 2. So now I've got my velocity pressure. And what am I going to do with my velocity pressure? What do I do with that number? Yes, I'm ultimately going to get my CFM, but I'm going to use that to get my velocity, which was 4,005 times the square root. Okay, that same information, to me, I don't know. This looks a little cluttered. I hope that other one presented it better. But this is just showing the same thing. Static, total, and then both of them hooked up for velocity pressure. Okay, like I said, that was for a positive pressure situation. If I'm on the suction side of my fan, this is going to be a negative pressure. You're going to want to hook that up to the low side now, because else, if I hooked up to the high side, it would actually suck the fluid out of it. So you got to pay attention to which pressure are negative or positive. Does that make sense? I'm negative. I'm negative of the atmosphere. The atmosphere is actually going to push the water back up, and you don't have enough room. You would actually lose fluid potentially if you hook up on the wrong side. And over here, if I'm on the positive side, I'll get it up on the high side. And this pressure is more than atmosphere. It's going to push that water column down. This pressure is lower than atmosphere, so atmosphere is actually going to push. Atmosphere will push the water column down there. Good with that? Yes? No? Yeah. Where would I take those readings? Well, we already talked about one. We're definitely going to take it across the fan. Our spec says you have to do a static pressure profile. It says to take pressures in a lot of different places, but places that would definitely be important potentially is across dampers. 5 is across the filter. 6 and 7 are across my coils, and all those numbers might benefit me. I'm going to check that against what was submitted. I'm only going to find what was the pressure drop across my cooling coil from my air handler submittal. If I'm not moving enough air, I'm going to start going back and looking to see, do I have any excess drop somewhere? Any excess drop means excess resistance, means I ride up that fan curve and I don't move as much air. You know, I said that fast. Does that make sense? Ish. Extra resistance means less airflow. All right, I meant to move this to the front because this kind of goes along with what we were talking about earlier. How close is close enough, right? Our spec says 5%. But that's only for the actual measurements. I measured this diffuser right here. I need to be within plus or minus 5%. There's some of this stuff that isn't dictated by the specs. One thing to keep in mind, not all is perfect. And this is actually in an ASHRAE standard. Good design and installation can provide adequate results in performance. I find that wording interesting. Same thing down here. They made it a lot longer here. So this was the 1988 version. They had to get more verbose in 2008. When the proper conditions exist, good engineering practices, realistic ratings, and good craftsmanship installation, adequate results can be obtained. A lot of caveats there, right? Even it kind of goes back to that whole we're trying to satisfy 80% of the people. Everything's not perfect. Sometimes you are going to have to be close enough, which was the point of this, kind of the middle of it. Should have been up front. ASHRAE Standard 111, it is a test and balance standard given by ASHRAE. It's got a lot of the same information as those two books. I held up the actual tab standard. So you could actually choose to use this as your tab standard. We don't. We say go by whatever standard the tab company we're using goes by, either AABC, NBB, or also TABB is another one. I've never seen a TABB contractor. This is a good document also for the design guys. It's got a lot of information on design considerations for your designs, how they might impact balancing and results in the end. It has a lot of procedures, the same things. So tab procedures, what is the tab guy supposed to do first when he gets on the job site? That's covered by a procedure. It's in those two books I showed you. There's other procedures in ASHRAE 111. Unexpected pressure losses. That's talking about system effect. We're going to go over that too. System effect.
Where do they publish that standard? I mean, can you just pick that up online or?
That one is available on IHS. 111 is, yep. Okay. The only standards I've ever found that I needed that I couldn't get on IHS were those two tab standards right there. I think just about everything is on there. Okay, so we're not going to talk about this a whole lot, but it's important to know that it's there. And depending on the inlet and outlet conditions of your fan, you might have some unexpected losses. Ideally, we want as much straight duct into and out of our fans to get the rated performance out of that fan. The designer should be looking at if he's going to have system effect and accounting for that in his equipment schedule in the means of added static pressure. The end result of evaluating system effect is, do I need to plug in a number to account for some extra resistance? And this standard can tell you much more about it than I ever could. If you really want to dig into this, AMCA 201, that one's also available on IHS. I'm going to show you what I mean by effective duct length, elbows at the inlet, and blast area over outlet. Those are the things that go into, or am I going to have system effect that I need to worry about? So when the fan wheel is spinning, you know, the outside portion of the fan, the farthest tip of it, is going to have the highest velocity. So I'm showing here. And it's going to take a little bit of duct before I get a uniform velocity profile downstream of that outlet of that fan. And you'd actually have to know, most fans are rated with a certain amount of duct attached to them. I can't quote it to you. But fans are not rated with, I have no duct coming off of it, or you need to have the submittal to know if it was. And what you'll actually find out going through this process is that if you actually have no duct on your fan, you'll actually probably get less airflow. Well, you will get less airflow than if you did have duct on it, at least to whatever your effective duct length is. I want to say that's 2.5 duct diameters, I think. Per that 201 standard, it tells you what effective duct length is. And so if my duct is shorter coming off of this fan, then it needs to develop this full profile. It's actually not going to perform as well. That's dictated by if the fan has this little cutoff in it. Obviously, the less surface area that I have on my duct, and I'm going to have a duct connection here, but you can see that the actual area leaving the fan is a little bit less. You would have to have that off. You have to find that on your fan submittal if that exists. This is just kind of showing that in 3D. So here's your total size of your fan outlet, and there's a cutoff inside of it. Anything else we want to talk about there? No, I think that's it for that one. You may do an example of this in your lab. But basically what you want to do is, let's say I'm going to have only 25% of whatever my duct is supposed to be. And if I know my blast area, my outlet area, I'd have to have fan data. I'd have to have my submittal to know this information. Say I'm at a 0.7 and I'm only going to have this much duct. I come up with a U to V, and I go look at another chart and I find U to V here. And I'm going to plot whatever the intersection is of my velocity. I'm going to have to know my velocity. Let's say I'm doing 3,000 feet per minute. Bring that up to my U curve. I would need to account for an extra quarter of an inch or so of static, if those were my physical conditions. Again, this is a design consideration. We're mentioning it though in case you run across a fan that's not doing what it's supposed to. You might want to look and see if you had some of these conditions that might have not been accounted for.
So what is it? You want to go over that chart again?
Sure. So I looked at, let's just pick another example. Let's say my duct, say I can't fit whatever size duct is this needs to be. I think it's 2.5 duct diameters, the equivalent to 2.5 duct diameters. I think that's what it is for that standard. But let's say I only have enough room to do this 75%, okay? And I would need to know my velocity. I know my fan's going to make whatever air it is. I'm going to know my velocity. Again, this is a design consideration. Designers already came up with, I need X amount of air. Now I'm trying to figure out what is my resistance that my fan has to overcome to get that amount of air, okay? So I only had, I think I'm missing, I think I said 75, but we'll just go with 50. So whatever my duct size was, whatever my limitation was, I would also need to know my blast area, my outlet area. And you can see if I have a one-to-one relationship, I don't have any consideration. You have to know your fan to know if that's your case. But just for grins, let's say it was 0.5 for whatever fan we have, and my duct dictated that I was only going to be this big compared to what I needed to be the 100%. I have the W. Now I come find W on this chart. It's here. Okay. You can see that as the letter gets lower, it gets worse. So this would be worse. So I'll go over that in a second. So if I'm operating on W, if I'm below, this is 3,000 feet per minute. If I'm below 3,000 feet per minute, it's not even on the chart. I'm not going to worry about it. But say in my example, I'm at 4,000 feet per minute. I bring that up to my W. Bring that over to how much loss do I need to account for? I need to account for about 0.17 inches of loss. I would need to have that added into my equipment schedule for that thing. Is that okay?
You said W, you went over X.
Sorry. Process would be the same either way. Find whichever one you're on, and just kind of the points being that, look at, if I have no duct, I might be on P instead of W. Well, what does that mean? For that same, where's P? P is here. So for that same velocity, whatever, I think I said 4,000 on P, well, now I got to account for 2 inches. Did you follow that?
So that would be in the design.
A designer would have needed to have accounted for this. He would need, if he had that condition, hopefully he didn't, he would have needed to increase whatever resistance he was going to list his fan to overcome by 2 inches. He calculated my duct is going to cause all this loss, my fittings are going to cause this loss, my diffusers are going to cause a certain amount of loss. He's going to need to add in an extra 2 just because of system effect under that scenario.
Is that kind of fan, or is it pretty?
That's specific. Yeah, well, the physical characteristics is going to be, this is going to be specific per fan. This is going to be by how you designed it.
So since he can't sole source, he just has to make a good guess.
Correct. Yeah. Look at what's available for your application, right? All right, everybody good with that? Speak up if you're not. So not only does it matter if I don't have enough duct, it also matters if I put a fitting in that space as well. So here we are back to, I need whatever it is, 2.5 duct diameters. If I put an elbow in that space, I'm also going to have that same system effect consideration. And it matters which orientation I put that elbow in. So thinking back to that chart I showed you before, the velocity is going to be highest here. It's going to kind of go down as it first comes out of the fan. So which of these do you think is the best arrangement if you got to have an elbow in this area?
A.
A is gonna be your best one, right? That air is gonna kind of hug, if you will, here, versus if I do this one, that air coming off the top of this fan, basically gonna smack it against right there. So you're gonna see, if you were to go look at the charts that give you the P's and X's and W's for these arrangements, you would see that this one has a better situation than this one. Where this also matters in the field is I can order an air handler with this fan in different orientations. So if the designer has said, install the fan upside down, the contractor says, well, that sounds really stupid. Well, it may have been to account for this, right? So you can order them in any number of orientations inside that air handler, something to pay attention to during your submittals.
Now, that only matters if you don't have 100% effective length for it.
That's correct. Yeah, you go back and look at your chart. I don't think you might do this in the lab. I think you go through a system effects part of the lab, but you would need to go find, like I've got them here for inlet elbows, you would need to go find whatever the chart is and evaluate that for your situation if it matters. And you might find that, yes, it's not just the effective duct length, it's also velocity. And if I land on an X until I get to a 4,000 feet per minute, it still doesn't matter. Or at least it's not 0.1. Also matters on the inlet. This is basically the same situation here. And what the point of all this is the type of elbow on your inlet matters. Not only does the distance matter, but the type of elbow matters as well. So remember that the lower the letter, the more resistance. So a square elbow, we're in the N to S range, and a radius elbow, we're in the S to W range. So these are less resistive, so they give you less system effect. They give you better flow condition coming into your head. Same thing here. You got all these are getting better. If you were to go look at these, we went from mitered elbows on this. I just went back. So we went from mitered elbows to turned radius elbows. And then what is also interesting, the type of inlet vanes don't matter from a system effect standpoint. See, these letters are the same as these letters. So if you had short ones versus long ones from a system effect standpoint, it doesn't matter. I assume it would matter on your whatever the designer is calculating overall, but it's not a consideration for a system effect. I think that's the end of the system effect. That's really just trying to convey that it exists. Designers definitely need to go research a little more into it. If you haven't been, for field guys, the takeaway is the inlet and outlet conditions as the contractor builds it matter. You know, if you had a certain dimension shown, make sure you meet that dimension. And again, if you really want to dive into it, go read that to your heart's desire. It covers it in detail, gives you lots more graphs, lots more situations. All right, shifting gears out of system effect to system airflow. So we talked about, we measured pressure earlier, now we're getting into airflow. We're talking about cubic feet per minute again versus liters a second for SI. And I want my actual airflow after accounting for density. So remember we talked about standard conditions, it's 70 degrees and sea level. So if I'm outside of, I think you showed a slide earlier, if it's down to 40 degrees or up to 100 degrees, I don't care temperature wise, I think 2,000 feet of my elevation where I got to make some sort of correction. How do I measure airflow? Well, for a duct, I can use a pitot tube or a hot wire anemometer. I don't think I have an example of that, but it's a little device. Same way that an airflow station works. Basically, it's got a liquid element, and depending on how fast the air is moving, it'll move a certain amount of heat from it, and it'll give you your velocity. If you see the little Ebtron outside airflow stations, it's the same principle that operate on, but it's just one point. You could also do a traverse and measure velocity in your duct using one of those. Flow hood to measure air for a diffuser. Everybody, I'm sure, probably seen one of these. It just spits out your cubic feet per minute. If I don't have a flow hood that'll match whatever my size grill or diffuser is, I may have to use a vane anemometer, something like this, stick it up on whatever's moving air. It would spin this
It would give me a velocity, I have to calculate my airflow rate. You have to have some kind of a correction factor. If you're doing this, I'm pretty sure y'all do this in the lab on fan code. You forget to use one of these.
Hey, man, on those right there, that's another place where it's really important that the air hits the diffuser square, because you can get, air drawn through the side that's not flowing out, and so your airflow measurement may be higher than what's really there. So just know that it's real important that you have uniform, but the air's all coming out.
You know, if you want the center, you might see a difference in the reading. Is that what you're?
Well, no, I saw, now that too, but on the anemometer, the hood catches all the air and brings it through, and there might be some strange things because it's got out of the grid. But on the anemometer, if the air is coming in, is getting drawn into one side of the diffuser, and that will actually happen inside both amounts coming out the other. So you'll measure both amounts if you're not careful.
Yeah, you would not want to use that on a diffuser like this. You want to use it against a flat grill or register, or a coil inside of a unit. If you don't have a good place to do a traverse, you might have to go in and use that all the way across a coil on an air handling unit to come up with the velocity. And you're going to take multiple points to get an average across it. And like I said, you're going to do that. Question?
That's what I was just gonna say, is that a multiple point with an average?
Yes. And they do make different sizes of hoods to attach to. That's why this is, if shape and size is okay, you're kind of limited on whatever the manufacturer gives you for those flow hoods.
Now, you can go linear with 1/2 and 1/2.
Correct.
I haven't tried.
Yeah.
I might mention too, they have an incredible range of hoods to go with those things. A lot of times they'll come out and say, we'll just block off part and use cardboard as part of it. Be careful about that. Because they can get the right size there.
All right, I showed you a lot of these, but the PO tube goes in conjunction with either a manometer. In the field, you're actually going to see some sort of differential pressure instrument, electronic one. I actually did, and I have seen a guy come out with, not with a manometer, but did come out with a magnetic helix. Every time I know they get a more accurate device. I did actually have a tab guy show up with a magnetic helix versus a digital instrument with the accuracy required by his own tab standard. The tab standard actually tells you if you're going to measure differential pressure, you must have an instrument that reads in like 0.001 increments. Obviously, you can't do that with this. This is just a manual device, just like a manometer. You see how sensitive it is? Just move it around. But yeah, I actually had a tab guy show up with one of those one time. A question?
I said low is better. Cheapest price.
Very true in that case. We talked about the main anemometer, which will give you a velocity. Flow hood will give you a cubic feet per minute. It's actually, again, it's sensing velocity pressure. It's calculating velocity and then also calculating cubic feet per minute because it knows the area that it's calculating or that it's measuring that from. And there's the hot wire anemometer, which I don't have an example of it. There's a little heated element right in there that will, as air moves heat away from it, it calculates the velocity and will output a velocity for you. And I kind of just covered most of that. We'll go back through it. PO tube, give me a cubic feet per minute, same as a hot wire anemometer, same as a band anemometer. And I would need to know, and just like he said earlier, your instrument may or may not give you feet per minute without having to go through the calculation for velocity pressure. And just another example. So if I measured velocity pressure and measured velocity, and I came up with 100 feet per minute, and I'm on a 10 square foot duct, I multiply velocity times area to get my flow rate. 100 feet per minute times 10 square feet of duct is 1,000 cubic feet per minute. And the instrument that always measures cubic feet per minute is going to be your flow rate.
Also, I didn't see it on the slide, but sometimes they can also take the grid out of those flow hoods, the no grid, and use it like a main anemometer.
Correct. Yeah, if you're wanting to do, let me have that. Let's see what's in here. No, it's not that. Yeah, you can, they have a way, you can actually detach this piece from it and hook it up to either a PO tube or a grid that'll let you not have to take quite as many measurements across the coil or something like that, give you a better average. All right, now we're gonna talk about a little more detail on a PO tube traverse. And just re-emphasizing correcting for density, and you have to correct for altitude and temperature potentially, depending on where you're at. And the tab standard tells you how many measurements do I have to have. So for a 4-inch duct, I need 2 holes. For a 100-inch duct, I need 10 holes. And I'm going to basically do the samples through that duct to come up with an equal. I'm doing an equal area method. I'm measuring, and I do the same thing for a round duct. And you'll see these are spaced a little different, but I'm coming up with a velocity for equal areas within that duct. And once I measure this velocity pressure, I get calculate the feet per minute. Then I can average all of those feet per minute readings that I get. I don't want to average the velocity pressures. There's that square root in there. You come up with the wrong number if you average the velocity pressures versus the feet per minute. But basically, you come up with an average velocity throughout your duct. And the number of measurements needed, or there is a requirement for that, how they're supposed to do that. Most tab guys probably know it. I would have to go pull up the book to know how many holes he's supposed to have and how many measurements he's supposed to take.
And be sure they give you the grid, because a lot of guys will try to just give you the average. And I believe any B now in their standard requires the grid, but watch for it. They didn't used to, and we get the averages, and you really need to see the velocity profile.
About the tab report?
Correct. Yeah, so the most often you're just going to see the final number. You can actually get all the numbers if you want.
And our standard and the tab standard says we do.
Yep. And you're going to do a traverse in the lab. So you'll actually
The really bad thing, things that used to be this way, but more and more of the technicians that go out don't really know what they measure. They just, and in some cases, the stuff gets electronically moved right back to their files. And so they'll, a lot of times, never even say, "Okay, we'll look at it." And so they can just give them the junk and get them out. They don't.
Okay. And you'll go over in the lab, they'll go over specifically with you in more detail. You actually do one, and the procedure you're going to get over there, we'll walk you through it. Basically the same thing for a round duct. The point being, how many measurements do I need to have and where are they? Depending on which size duct you have. I mean, you'll notice he's not supposed to take one in the center for the standard. The standard tells him how far apart are your readings. You'd have no way of knowing if he did it per that, if you don't get each individual reading, how he laid that grid out.
Why don't you measure the center?
I guess it's got to be with how they're, the velocity is going to be much higher in the center. So I guess however they came up with, this is what our equal area average is going to be, they chose to leave it out. I don't know. But that same process is in all the tab standards as far as how you take that. You don't get one in the center of a round duct. Whoever did the math originally came up with that. All right, going back to this equation, and you are going to need to do this tomorrow in your lab. I keep talking about it. So remember, for standard conditions, 4,005 times the square root of velocity pressure. And where do we get velocity pressure from? Traverse, right? And standard conditions. If I'm at other than standard conditions, I got to find my density at that point and do a correction. And actually, I think this says, this might be from Ned. I think either way, and you have to know what your tab standard says if they were required to make a correction or not. For almost all of us, we probably don't have to worry about that unless you're over 2,000 feet or if you're doing it in potentially a really cold winter. All right, so please don't look at your books. We're going to do some examples. Oh, wait, hang on. I think I'm not there yet, am I? Well, no, these are already in there. Sorry. I thought I had that broken up where it didn't give you the answer. All right, so let's just walk through this. We're going to show you how the correction for density matters. So my first reading, I'm at sea level, and I would get this density from another chart for sea level at 70 degrees. I did a traverse, and I came up with 0.0623 inches of water column. Plug that into my equation for standard conditions, come up with 1,000 feet per minute. And in this example, I have a 1 square foot duct, so doing my velocity times my area, come up with 1,000 cubic feet per minute. Is everybody okay with that? All right, now I'm going to go do that same reading at a 2,900 foot altitude. Now I'm going to correct for density. I have to look up in a table what my density is at that altitude. We're still at 70 degrees. I've measured the same velocity pressure, okay? So yep, measured the same velocity pressure. Now I'm going to correct for density. So I have to use that other equation. It's not the 4,005. Plug it in for my density. Come up with 1053 instead of, what was it, 1,000. So I had a 5% difference if I hadn't corrected for density at that altitude. Now let's go to Denver and do the same reading, 6,000 feet, 70 degrees, same velocity pressure, plugging in that different density in this example. Plug your way through it, 1,100 CFM. Everybody okay with that? Let me show you that table. So this is just a table. What your error would be if you don't correct for altitude in those places. We got anybody here that's above 2,000 square feet or 2,000 feet? Yeah.
Yeah, project of 14.
So most of the instruments are probably going to correct for it, but it might be a question you want to ask. Might want to find out. If you're ever in those locations, I'd be asking my tab guy to make sure his instrumentation is corrected for it. All right. How are we doing on time? Break time? 5-minute break?
That's gonna be fun.
Good question. Yeah, that's better. Within 30 degrees. As far as
Okay, because in this factory, well, I'm trying to ask you. Well, now, we're right there. Sure. If the larger that, then you have one of that area.
Who was sleeping? Eyes will be sleeping.
So when I had an operation, like an office for it.
Well, why did you just got a lot of topics?
I know. I'm used to it.
And work out on the hard part first. That was easy the rest of the day. This one, this is like that on a daily basis.
It's a big difference.
So if all those underfloors and viaducts we got, I guess we're gonna have to traverse all that. If there was a flow rate listed for each one, yes. I don't think there is. I guess one of the problems I never have right now is we don't have a specified flow rate. Yeah, certainly, if we just call out.
Yeah.
What's the point of putting dampers in? If you wanted to shoot that air throughout the system, I would have thought it had 90% flow rate. Yeah, I think they're still going back and
I
talking
hope
about
that
it.
we get this, this is a really nice section. That'd be, because you don't find them this large. And it's,
But I'm kidding.
yeah. This is really go through any of this stuff.
Yeah. Some of the material they put together for the class.
Right.
And they probably should ship themselves.
Of course, there is class.
Can't wait to remember what floor you're good to go.
So maybe I'm gonna go ahead and get started. All right, shifting to fan laws. So if I need to make a change in airflow rate, going back to my example where I had the shiv drawn up, if I need to change the shiv, and I'm not moving enough air, and I'm either gonna change the shiv size or speed up or slow down through BFD, how do I figure out what setting or how much I need to change it? And use the fan laws to do that.
And so I'm going to show these in a little better format in just a second. I'll show them, at least they, to me, make more sense in that format. But just to kind of summarize them, there's a direct relationship between my flow rate, my CFM, and my fan RPM. So if I make a change in fan RPM, I will see a corresponding linear change in CFM. As to where with pressure, if I make a change in RPM, my change in pressure is actually going to be with the squared relationship of that. And the kicker is horsepower, which you can equate to current, is cubic. And we'll show you how those numbers work out in just a minute. And keep in mind, this only applies when resistance to airflow is constant. So my set duct configuration. If I go start moving dampers, and I don't have the same system curve anymore, this only applies on one system curve, like I showed you on the fan curve. And this is just rearranging those terms that I just showed you. So there's also a linear relationship with the sheave diameter. So you could also put equals RPM over here. And I probably need to do that, but well, here it is right here. So RPM and sheave, CFM and sheave, they're all equal. And the same thing, I can just substitute terms. You know, so on this sheet I had RPM squared with the relationship between RPM and static pressure is squared. Same thing, I can substitute CFM for RPM because those two terms are equal up here. And same thing, if I make a change in cubic feet per minute, the horsepower or the amps are equal. The change in amps are going to be equal to the change in horsepower. That's a cubic relationship. And we're going to go through these to hopefully make a little more sense. So to get these in a usable form, I'm going to go measure my flow rate with whatever means I do it. And I'm going to measure my RPM. So what I know is subscripted by 1. I know my cubic feet per minute, and I know my revolutions per minute on whatever piece of equipment I'm looking at. And if I'm short on airflow or high on airflow, I also know what I want to change my airflow to. So I want to calculate what RPM change I'm going to make. Okay, so I'm trying to solve for RPM 2. With the example that I'm walking to, I could rearrange terms. Basically, I just multiply both sides by RPM 1. Put RPM 1 over here. That's what I'm looking at here. So I know this flow rate. I know this RPM. I'm figuring out for my design schedule. You know, we'll do an example in a minute. Let's say I have 7,000. I need 10,000. And I measure this. I know I need to change it to get that 10,000 CFM. All right, so here's an example. Here's what I was looking for. Please don't look ahead. I'd like you guys to walk through this. System air volume is measured to be 30,000 CFM. And I measure my revolutions per minute at 1250. And I want to get 34,000 CFM. So I'd like y'all to walk through that calculation. Remember, it was RPM2 over RPM1 equals CFM2. That's probably hidden. No good. CFM1. Sorry, I can't see that.
So we're trying to get to CFM2.
We're trying to get RPM2. I gave you CFM2. The design called for 34,000. You got 30,000. Right? Anybody got a number? That they want to look up? Sounds right, 1417. So plugging those in, starting with my base equation, I wanted to solve for RPM2. Just multiply both sides by RPM1. That's how I got to here. Going back again, what I knew was subscript 1. I measured 30,000 CFM. I measured 1250 RPM. What I want to get to, my design, was 34,000. Plug those numbers in. I need to change from 1250 RPM to 1417 RPM. And think back to our fan curve where we were talking. That's certainly in range of the fan curve we were looking at. We were like right around that 1200, 1300 RPM range with where we were looking at on that operating point.
Okay, so I need to make that change. I can do that either with a change in the sheave size or if I have a VFD, speeding up or slowing down the VFD. All right, please don't look ahead. Existing fan sheave is 18-inch diameter. In this example, we're going to change the fan sheave, and I want to get from 1250 to 1470. That's the number that we just calculated. So let's go back a little bit. I'll show you that number. So here we are here. So let's use that equation. It was 1417 over 1250 and 18, right? I think.
15.87.
Right. Sheave size went down. Okay, so I'm changing the fan sheave. All right, does that make sense? I want my fan to spin more, so I got to put a smaller sheave on it. I'm not changing my motor sheave, I'm changing my fan sheave. Are we okay with that? All right. Now we're going to calculate what does that do to me current-wise. What relationship did fan cubic feet per minute and current have? Cubic. Right, so now we go back to I'm sorry, I didn't let you. I probably didn't go. I don't have to get the amps to that. We are initially at 30 amps. The same numbers, 1250 RPM, 1417 RPM is what I want to get to, and I want to calculate what's that going to do to my current. And that's here. Anybody? Big number. So because of that cubic relationship, I went from 30 amps to 43 amps. So what sounded like not that big of a deal RPM wise, would this matter? Would this change matter?
Oh, yeah.
Very likely. What all could that impact?
Overloads, wire size.
Everything. Breaker size, probably even in a different breaker size, conductor sizes, disconnect size, everything could potentially change. Motor size could potentially change because of that. So that's where you got to be careful. Going up in airflow rate can be dangerous. And this is just showing that percent change. So a 13% change, and we went from 34,000 CFM, excuse me, we went from 30 to 40, 34,000. That was only a 13% change in airflow rate. But we went from 30 to 43 amps. That was a 46% change in current. So no, in general, if you're that much short on your airflow, unless your motor was really oversized, you're probably going to be in trouble with that motor anyways, and potentially your electrical system going through it.
If you've got a VFD and you say ramp it up,
You'd be in the same situation. Yep. It takes that much power to move that much air.
because I hear people all the time saying, well, let's dial it up.
Which you can, as long as you're not exceeding your electrical system rating or your motor rating. Or we also talked about that fan curve earlier. We had the class 1 and class 2 fan ratings on the fan curve. I'm going to show fan curve again in a minute. Make sure you're not exceeding your fan classification as well. This is just going back and showing you the relationship with pressure. So there's a squared relationship. If I make that same change, I'm going to see if I double my RPMs, I'm going to have 4 times the amount of pressure. And then I can rearrange those terms to figure out what it is I'm solving for. Most likely, if you're using this, you're probably trying to solve for some static pressure. We'll do an example of that. So I go out in the system and I measure static pressure. It's 0.6 inches.
And most VAV boxes, this is kind of realistic, need at least 3/4 of an inch on the incoming side to operate correctly. And I was back at that same number of 1250 RPM. So in this instance, I knew static pressure 1, that was 0.6. I measured 1250, that was RPM 1. I'm figuring out, I was given, I needed to get to 0.75, plugging those numbers in. There's a corresponding change in RPM I'd have to make to meet that static pressure. All the point being, you can rearrange those terms to figure out where you need to be.
Before you do all this though, I mean, if it's, you need to back check everything leading up to it. I mean, that seems
yes.
like, I'm no mechanical engineer, but it seems like all the meetings I've been to, it always seems like these mechanical tab guys are always putting Band-Aids on things.
Yeah.
You know what I mean? Like they get to the end of one, it's like, oh, well, we'll just do this. And it's like, what about all the shit behind it?
Yes.
You know what I mean? And
Correct. So yeah, I would want to know, I would want to ask the question, why am I needing to do this? So that's kind of where that information talked about, the static pressure profile. At this point, yeah, I'm going to go look at, do I have any excess resistance that I wasn't expecting anywhere through my system? And it could very well be, like we have on a project right now, that our designer busted and all our ducts were undersized. May not be the tab contractor, the contractor's problem. So keep that in mind too. They put 15 foot of flex on the end instead of 5. The whole thing was undersized. We're still trying to figure out what we're going to do actually.
You pay for it and the designer's off the hook.
That's right.
Use your contingency.
Yep.
And pay for their mistakes.
Unfortunately, yep. I mean, we messed up when we put it out wrong. We own it at that point. And again, the point being, it may not be the tab guy's fault. Often is, but it may not be. And just going back to that whole static pressure, that's a good question. Right in line with this, I can measure. Maybe they got the wrong kind of filter there. Maybe they gave me too good of a filter beyond what I called for, and there's some extra resistance there. I don't know.
I probably got a lot of construction filters.
Could be. Who knows? We had a cash register end up in a duct system one time because the dining facility next to us got broken into, and they literally threw the cash register into our duct system. So you never know what instructions you might have in your duct system. That's a true story. In the chapel, by the way, they robbed the defect, threw the cash register in the chapel ductwork system. Another talking point on this slide is too, like we were saying on this example, I measured 0.6 and I need 0.75. So if I've got my air handler and I've got my duct system and I go out to this farthest VAV box, I need enough static pressure to get the air through this box. I might have to increase my fan speed to do that. So that's kind of what that example was. I need more pressure generated at this point. I can calculate, if I knew I have 0.6 right here, I can calculate what do I need to do with this sheave to get 0.75.
And then go back and retab everything else.
Correct. Well, everything should be proportional at that point. They should have already. We're going to talk about proportional balancing as well. Right now, we're still talking about the air handler, pretty much the essential piece of equipment. I kind of said this earlier. Just the point being that if I double my static pressure, if I have 1 inch, I double the fan speed, what happens? So I double my fan speed, square it, I actually get 4 times as much pressure. I don't think I have an example of that, but the same thing would be for current. What if I doubled my fan speed, what would I do to my current? The Q would be 8. Right? And there's that equation. Don't think I do an example of that, but you get, again, double this, it's going to be 8 times higher. All right, summarizing all that, we can predict changes in the system based on these equations. And I'm predicting a change. I showed you the system curve. I'm going to change my I had my fan curve that was going this way, had my system curve going this way. I'm going to change the revolutions per minute that my fan was operating at. I'm going to ride up and down that system curve. Again, damper positions can't change. So in a VAV system, dampers modulate all the time. I never have a set system curve unless I go in and lock those damper positions down. Big takeaway, power gets consumed quickly. That cubic relationship can really hurt you. Questions? Fan loss? Motor measurements, talking about that current going up. So what am I looking at? This is the same picture we showed you earlier. So, submittal wise, I definitely want to check that I have the right motor in place, that it's big enough to handle whatever load it is I need. We saw on the system curve, the fan curve, what size motor I needed for that. That motor size should also be specified on your equipment schedule. You want to check that your horsepower rating is adequate. You need to make sure which voltage you're operating at. This one says 230 and 460. What does that mean? It can operate at either one of those voltages. It's got different taps on it, depending on what voltage your system's going to be. And correspondingly, the amps, if I'm running at 230, it can go up to 2 amps. If I'm running at 460, it can only go to 1 amp. Okay. This motor is rated for 1725 RPM, but I can attach whatever size sheave I want to it and get a different RPM on my fan. Most of the time, our specs are going to call for a 1700 RPM motor. You could put a larger one in. You could do 3600, but especially noise can be a consideration if you start getting the larger motors that are spinning faster.
On these, also in 3-phase, we get all the measurements from all 3 phases. And one of the things you need to watch, I think it's the amperage. I think it's a 5% difference. We're okay, or that motor life starts to go down pretty drastically. On new construction, that's something that might be addressed, might be a motor problem. On existing construction, if it's not a motor problem, it's probably working in an area that you're not doing anything other than electrical, you're probably stuck. But just be aware that that's one of the things that off the tap guys, again, just give you the average. You want to see all 3.
Yeah, so they're going to measure on a 3-phase piece of equipment. You got 3 legs. He's going to use a clamp-on ammeter and go measure each leg individually. You'll get a separate amperage reading on each one of those. So none of those can be over the rated amperage, depending on which voltage you're at. And then I don't know what the number is, either 5 or 10%. They also can't be any more than 5 or 10% apart. They won't be exactly the same because your voltage is going to be a little bit different on each leg. But yeah, the tab standard does cover how different each one of those can be. And probably talking about electrical distribution system problem might be a motor problem if you had a substantial difference between current or voltage on each leg.
Yeah, and NEC is actually where they address the issue of the difference in how serious it is.
And important thing to talk about, I mentioned that you can't exceed this number. Every motor has what's called a service factor. You've probably heard your tab contractor say, just going back to whatever that example was, we'll just speed it up a little bit. Well, we'll just be the service factor a little bit. It'll be all right. No, never. Contractors are going to want to just speed something up and run it in the service factor. And the service factor is a number that, according to the manufacturer, this motor can run up to 25% higher than its full load amps and not die. But it can't do it for forever. If you go read the NEMA standard for motors, it'll tell you don't exceed it permanently, but it's okay short term. So it allows for problems on your distribution system, basically, changes in voltage between phase to phase. But you should not be running a motor in its service factor permanently. It will decrease the life of the motor. The NEMA MG1 standard for motors that all the motor manufacturers build their motors to say that. If you got a contractor arguing with you, go pull up the NEMA standard for motor and show them that paragraph. And I think it even says it in A and B, C as well. I don't know about ABB.
And with that, so it doesn't blow up the motor in initial start, because when it initially starts, it needs more power. So I think it gives it more power, but like you said, not for long.
Correct.
It's only a startup.
Well, and even your startup current is going to be higher than that 25%, but it's built to withstand that. But this motor is definitely not built to withstand running at 3 amps for forever at 230. It'd be too much, or even really whatever 2 times 0.25 is. So if you haven't heard that situation, you're going to have a contractor ask you, can we just run it in the service factor? And the answer is no, you cannot. You need to get the next size motor up or go back and figure out why am I needing this extra power to do that. What else? That's probably it on that. This was a 3-phase. We talked about single phase. You might just have a 120 fan motor as well, or 208 single phase. All things to check during your submittal phase. Kind of showed you that. We checked volts with voltmeter, showed you the ammeter, and hopefully you never have to see one of these. Harmonics analyzer. I've had one project where we had to have one. There's a problem with checking voltages and amperes. We've got an electrical guy in here. Maybe he's going to help. I get outside of my realm of expertise, but because you're going through an inductive load, you've got a power factor associated with reading the volts and the amps. So power consumption for a motor is not as simple as volts times amps.
That's also tell you when you're in regions you need to deal with, maybe totally avoid. So that's real important on the VFD application.
You'll see this meter being an RMS, root mean square. You definitely want to see the meter that they're using is a root mean square meter, because else it's just doing some calculation to give you your current is a sine wave, and a root mean square takes that into consideration when it gives you a number, root mean square meter versus cheaper one, which you should never have a tab guy show up with a cheaper meter. I'm not sure how it determines it, but it's not right. It's not. This is what we require. This is what the tab standard requires. Unless you're getting into some significant problem or having to do some sort of electrical capacity test on a big chiller or a cooling tower, you shouldn't need to know exactly what your power is to see one of these on your job sites, but you might. We had an example where not only the HVAC, but dryers in a barracks kept tripping the breakers for no known reason. They brought one of these out, I brought an oscilloscope out, figured out we had to put some kind of filter on that leg. It's the only time I've ever seen one.
That's what computers is. So.
Yeah, if you got some data center where your power is critical, you might need to have that. We talked about measuring RPM several times. How do I do that? You can do it with a stroboscope, so just a light, and they can dial it into however many flashes it's flashing, and try, if you want to look at a fan wheel that's spinning. If it's spinning at 1800 RPM, and I'm flashing this at 1800 RPM, it would look like it's sitting still. So that's one way I can determine revolutions per minute. Another way is to kind of do the same thing with the non-contact version of that. And these things are kind of magic in my mind, but basically you put a little piece of tape on the wheel that's spinning, point this at it. As it's rotating, it'll tell you what the revolutions per minute is. That's probably what you're going to see. Well, you can probably see both on the job site. And there is a contact style where you can actually lay it on the shaft and let. This is going to spin with the shaft. That's the most dangerous way, obviously. But if I'm not mistaken, I think I read it. Preparing for this class, I think the tab standard, that's the preferred method. I would never tell a guy to do it that way. I don't want that liability. All right, motor current. I've kind of talked about that a good bit. Don't exceed the motor rating. We would use the clamp-on meter around each wire to take that reading and stay away from the service factor. I kind of got all this stuff. True RMS, make sure you use true RMS. Talked about power factor. And like he said, when you go through a VFD, some funny things happen electrically. I can't explain it to you, but you're not going to get good readings if you're trying to read the power on the other side of the VFD. You have to be reading it on the top side of it, because whatever it's doing to create a different frequency, outside of my electrical knowledge, if anybody else has good knowledge on why that might happen, feel free to help us. But I just know that you can't do it. If you go read the voltage on the other side of a VFD, it's not going to be correct. It's not going to, well, it's correct for that motor C, but their VFD is changing the frequency. Also a piece of magic I don't understand. We operate at 60 hertz, everything in our electrical system, and somehow this thing is able to either take away or even add hertz, however we do that. So we're operating 60 cycles a second, and that VFD can make it operate at 48 or whatever it needs to, or it can actually go above 60. It can go up to 120 hertz, so it can somehow create hertz. Talked about the harmonics analyzer, and again, if you're needing some instrument where you have to know exactly what the power is, you have to use something like this, or they make another instrument as well. But you can see, they're pretty expensive. This line's pretty old, they're probably more than that. But for capacity testing for big piece of equipment, you might have to pull out one of these, because your power factor is generally going to be like 0.8 or 0.9. So you might have that much of a difference in your reading if you're not using a harmonics analyzer. But we're typically reading and reporting voltage and amperage. Big thing we care about both of them, but we're really trying to make sure we're not exceeding that amperage on the motor rating. Brake horsepower, and this is kind of comes into play. Like if I want to calculate brake horsepower, which is the actual power required to move the fan. So when I go measure current and measure voltage, that's on the incoming side of the motor. The motor has an inefficiency in it, and there's a power factor. So, I have to put more power into that motor than it actually takes to move the air. And that's where if I wanted to calculate brake horsepower, I would have to know my power factor, which your standard voltmeter doesn't give you. That harmonics analyzer would have to give you that. And I need to know the efficiency of the motor, which is published on the motor. But the efficiency of the motor changes depending on what speed it's running at. So, point being, for a motor, it's not as simple as volt times amps, like it would be for a resistive load. Resistive load being a heating element. The motor adds an inductive element to it and brings in this power factor. And that was for single phase. For three phase, it's basically the same equation, except you add a square root of 3 in there to account for the three-phase operation. Shouldn't have to do this stuff. Just wanted you to mostly be aware of this guy. If you're trying to figure out power and you're just using the numbers you're getting off a standard voltmeter, it's probably not going to make sense. Motor measurement summary. Be able to look at that motor nameplate. Hopefully you understand a little bit more about what all those numbers mean. And the big part being, we don't want to exceed the current that's listed on there. And so once again, contractor comes to you and says, I just need to get in that service factor a little bit. We don't want that. Questions? Motor measurements.
Because this is special equipment, like most of that require the latest calibration paperwork along with it when they come to test.
Everything does, and we'll talk about that tomorrow. Okay, so kind of bringing this back into the QA realm, what can we look at as construction progresses that might impact all those readings that we've been talking about? The type of ductwork. He showed you a slide earlier that showed you the pressure loss for a 144 square inch round duct is different than the pressure loss for 144 square inch rectangular duct. So duct size does matter. Contractor says, hey, we don't like round duct. We'd rather do square duct. We'll give you the same area of duct. Is that okay? No, it's not okay. And I've had contractors ask me that. Because round duct's more expensive. So no, you don't want to let them do that. Duct size changes. Same thing. We want the duct sizes that are shown on the drawings. Design build job. I had a contractor submit shop drawings. Designer had approved them. Apparently did not look at them because every single duct was smaller. And his reasoning was he was trying to keep, the contractor said he was wanting to keep the velocity the same. Designer had approved it. He didn't even look. They had actually, and then so, I said something, sorry. Make sure you're paying attention to the duct sizes and shop drawings. Do I look at every single duct size through the drawings? No, but I do look. Apparently that designer didn't because every single duct size had been changed by the contractor. His rationale being, I want to keep the velocity the same. No, that's the engineer's decision. He picked your velocities and how that duct was sized. He just wanted to put smaller ducts in, so he wanted to. Could have been a problem, obviously, that we went through. We talked about radius versus square elbows from a system effect standpoint. The same thing. You're going to see different losses between radius and square elbows just from a friction loss standpoint. Make sure you use whatever's called for in your drawings. We saw radiuses are going to be a lower friction loss. The type of branch duct takeoff matter. Our spec allows the use of extractors, which I hate. When I read that, I'm going to put in a request to change that. The tab standard actually says those things basically suck, but they are allowed. You never see them. I think we should get them out of our spec though. It says you can use use extractors, or you can use 45-degree or conical takeoffs, which is what you're probably going to see most of the time. But the specs actually do allow extractors. I would tend to go with.
We have them taken out.
What's that?
During the design phase, we have those splitters taken out.
Yeah. And you know, a lot of times you might see a detail in your drawings for what the designer planned on. Another thing for design guys to know is that the specs allow multiple types of takeoffs. Go in there and take out whichever ones you don't want. Because if you just show one style in the drawings, in the government world, the specs rule, right? The specs say you can use different styles. So please take those out, whatever you don't want to have.
What are extractors?
I'll find you an image of it. Can you write that down? I'll find.
I had to look it up, and that's my last.
Yeah. No, I'll post an image of that, but I'll have to look one up. It's basically a little scoop that goes into the ductwork to try to bring the air down. I've got an image of one.
Yeah, it's adjustable. Some of them are like turning vanes and swing on into the duct. No matter what they are, you don't want to.
Yeah, one of these things, as I was reading for the class, actually said, one of these tab standards says, these things suck somehow. I said that. Wow, that's great. Obstruction. So inevitably, I'm going to run into a piece of steel where my duct needs to be. And we've got smart ways that we can do that. You know, 4 90-degree fittings is more resistive than 4 45-degree fittings. Okay, so if you run into the situation, let's try to be as smart as we can out in the field with whatever obstructions we're going to create. And if you get
standard for that also.
correct, and if you run into this situation, if you start having to add a bunch of these, you also need to call your designer back up because he probably didn't account for a whole bunch of extra elbows that are going to add static.
And those are worse too, beside 90s, because the flow coming off the 90 isn't fully developed. And so his calculation for the ductwork pressure drops are going to be off. And the only question of how wrong, it's only a question of how wrong. It might be a little bit fifty rather than that.
Turning vanes, our spec requires them. Type of turning vanes, so depending on, I can't remember if we call for the long radius ones or not in the spec, but make sure you're paying attention to plans and specs on all these things that can impact how much airflow you're going to get at the end of the job. You shouldn't see acoustic lining. Our spec says not to use line duct, but every now and then it shows up. But key takeaway is acoustic lining. If a designer shows a dimension, you need to check your drawings for that should be the inside clear dimension. So your duct would have to be bigger than that to allow for whatever 1 inch or 2 inch of acoustic lining inside of it. But if I'm not mistaken, the HVAC UFC says not to do it.
You want STCs.
Right. Yeah, you might find a situation where you have to have it for sound purposes, but in general, the UFC says not to use it. Somebody mentioned flex duct earlier. I think our spec allows 5 feet of flex duct. You might see a detail in your drawings that might allow more. Definitely something that be coordinated and checked. And the installation of flex duct is also important. You know, flex duct that's just kind of drooping and got kinks in it is obviously a lot worse than one that's, if you look at the installation instructions,